Hello there and welcome to Life Beyond Seen, where curiosity settles in like a gentle tide and the strange wonders of the natural world drift close enough to examine without ever disturbing the peace of your evening. Tonight we're slipping quietly into one of the most unlikely places where life grows bold, vast and astonishingly large. Not in the sunlit shallows, not in the warm tropical currents that so many creatures call home, but far from them in the coldest waters on Earth. These places where the sea is dim and slow, where frost hovers at the surface and deep pressures hold the silence steady, are somehow the very places where animals grow to their most startling sizes. It feels counterintuitive at first glance. You might think warmth would encourage abundance and cooling would shrink everything down. Yet in these frigid blue depths, the opposite happens. Creatures swell in size, bodies stretch, limbs grow long and heavy, mouths expand, eyes widen, shapes sharpen. In the stillness of the cold, life becomes immense. Before we wander too far into those waters and the curious reasons they create giants, I'd love to know where you're listening from tonight. Are you somewhere warm, wrapped up and resting after a long day, or somewhere a bit colder yourself, feeling the seasons shift around you? And while you're here, if these slow explorations help you find a sense of quiet or give your mind a softer place to drift for a while, I'd be grateful if you'd like the video or subscribe to the channel. It helps this little corner of calm reach others who might be winding down for the night, or who might simply want to follow something steadily through the dark without needing to keep up with anything too fast. Now, as we begin to settle into the idea of icy oceans filled with enormous beings, there's something grounding about imagining the contrast. Warm waters tend to be associated with colour and energy and movement. Schools of bright fish weaving through coral, sunlight piercing through clear shallows, life buzzing, darting, flickering. Cold waters, by comparison, usually bring to mind a slower rhythm, heavy expanses of dark blue, long stretches of quiet, ice drifting, depths widening. The idea that something huge could be hiding there feels a little dissonant at first, almost like a secret nature is kept from us until we finally ask the right question. Yet long before scientists started cataloguing the astonishingly large species that inhabit these regions, sailors had already whispered stories about them. Reports of creatures bigger than anything found in the tropics, animals with eyes the size of dinner plates, limbs that stretched farther than any reasonable imagination, bodies that moved with the kind of heaviness that hinted at tremendous mass beneath the surface. And while many of those stories were embellished out of fear or wonder, or the simple challenge of describing something seen only for a moment, the underlying pattern was true. The coldest waters do indeed host some of the largest animals ever known. Even now, when measurements replace myths and cameras replace sketches, the truth remains just as strange. The blue whale, the largest animal to have ever existed, thrives in these cold, nutrient-rich waters. Colossal squid, once creatures of whispered exaggeration, are now confirmed to be astonishingly large and adapted specifically to the chill of the deep. Giant amphipods, oversized jellyfish, massive isopods, elongated worms, huge spider crabs, enormous sea stars, all find their best conditions in cold regions. Somehow the frost does not shrink life but expands it, almost like a sculptor that works with slow, deliberate strokes and needs the stillness to form such grand shapes. As we drift further into this idea, it's helpful to pause for a moment and picture the environment itself. Cold water is heavier, richer in certain dissolved gases, and more stable across seasons compared to warm water. That stability creates a kind of predictable rhythm where creatures do not have to hurry or scramble constantly to survive. There's something almost counterintuitive in the way that stability encourages largeness. In regions where everything changes rapidly, smallness tends to be advantageous. Quick reproduction, fast metabolism, the ability to dart away or hide in small crevices. But in the polar seas and deep cold, the environment moves at a slower beat. Nutrients follow seasonal cycles, pressure remains constant in the depths, and the cold slows down the internal processes of nearly every creature that lives there. Life that does not need to rush can afford to grow, and life that can move slowly without risking starvation can invest more energy into building bodies of impressive scale. But there's more to it than that. Cold waters contain more dissolved oxygen than warm waters, and oxygen is a kind of fuel for growth. Not the kind burned quickly like a match, but more like something that allows each cell to function more efficiently. The more oxygen available, the easier it becomes for organisms to sustain larger bodies. For many species, especially invertebrates, oxygen is the limiting factor that decides how big they can become. In warm waters, oxygen dissipates quickly. In cold waters, it saturates the environment. The creatures living there breathe more easily in a sense, and the result is an ecosystem where growing big is not just possible, but often the optimal choice. As we imagine these enormous beings moving through freezing currents, there's something humbling about realizing that cold can amplify life rather than diminish it. Many of the animals that thrive there do so with an almost serene slowness. A giant sea spider, legs extended longer than its tropical cousins by magnitudes, moves with a deliberate calm. Amphipods, those normally tiny, quick, shrimp-like creatures, become large enough in Antarctic waters to fill the palm of your hand. Isopods balloon to the size of house cats in deep, cold trenches. Creatures that in warm environments are nearly invisible take on new forms of presence. The cold sculpts them differently. But to appreciate why this happens with such consistency across species and across regions, we should keep following the path that leads deeper into the sea. Each region has its own particular blend of pressure, temperature, oxygen, and food availability. Yet the cold regions share a repeating pattern. Larger than expected animals showing themselves again and again. And as we observe them, the idea becomes clearer. Cold slows life down, but slowing life down does not restrict life. It redirects it. Energy that might otherwise be spent on fast movement or rapid metabolism is instead spent on growth, longevity, and endurance. Many cold water animals live far longer than their warm water relatives. Time gives them room to become immense. In some ways, it is the patience of the cold that allows giants to emerge. You might picture a creature drifting through the dim waters beneath ice shelves, its body heavy but unhurried. It doesn't need speed. It doesn't need bright coloration. It doesn't need the constant alertness that tropical fish display in their fast-paced ecosystems. It needs instead the ability to persist, to endure long stretches of cold seasons, to store energy, to navigate vast distances in search of food carried by seasonal blooms. That endurance is written into its size. A larger creature can store more energy, maintain its temperature or resist the surrounding cold more effectively, travel greater distances, and survive longer periods of scarcity. Size becomes survival rather than excess, and once size becomes survival, the path toward gigantism opens wide. As we drift gently through this idea, there's something compelling about the way evolution shapes bodies, according to environmental rhythms. In the tropics, speed and agility are rewarded, so sizes remain modest. In the cold, endurance and storage matter more, so creatures expand. Water itself behaves differently in the cold. It becomes thicker, more viscous, slowing movement, but also supporting larger bodies. Predators that rely on stealth or ambush can afford to grow larger, because they are not required to chase prey at high speed. Prey animals grow larger as well, gaining resilience through mass. Everything adjusts, and beneath all of this, there is the deep sea. The coldest place of all, unaffected by seasons, untouched by sunlight, and unchanging across millennia. Here the pattern becomes even more pronounced. Animals grow large for reasons that echo those of the polar seas, but with even slower intensity. Food arrives intermittently, but usually in rich, sinking pulses. Pressure is enormous, crushing, unrelenting, yet the animals that live there thrive with bodies that appear oversized for their low-energy lifestyle. Slow metabolism means every calorie must be stretched as far as possible. Larger bodies lose heat more slowly, resist pressure more effectively, and stretch their resources over long spans. In the deep cold, being large isn't just a quirk, it's the strategy that works. As we linger on this picture of cold oceans filled with immense forms, it becomes clear that cold does not merely host giants, but encourages them. It sets the stage for them to evolve, survive, and dominate their ecological niches. And as we move a little further, the question shifts from how the cold creates these giants to what exactly is happening inside their bodies, how their muscles, organs, limbs, and even cells operate differently in temperatures that would freeze most forms of life solid. But before we slip into the deeper mechanics of their biology, there's something comforting about appreciating the simple contrast. Many of the biggest creatures on Earth do not thrive in warmth, but in the cold. Not in the quick, but in the slow. Not in the bright, but in the dim. The cold, steady waters of the world are not empty or barren. They are full of enormous lives moving gently through environments that allow them to become vast, unhurried, and enduring. And as we drift further into this story, we'll start to explore how exactly these creatures grow so large in conditions that seem at first glance to be some of the most challenging on Earth. The cold has shaped them, and in doing so it reveals something unexpected about the nature of survival. When we move from the gentle surface chill into the true cold beneath, the kind of cold that settles into the bones of the ocean and stays there year after year, we begin to meet the animals shaped by it. Not creatures merely surviving, but fully adapted to environments where temperatures hover near freezing, where light fades to a muted glow, and where every movement feels cushioned by the weight of the water. These regions are not empty. They are not as barren as they sometimes appear on satellite images. Instead, they are home to beings whose sizes often catch us by surprise. They drift through these depths with a kind of calm heaviness that looks almost effortless, despite the enormous bodies they carry with them. The first thing that stands out in these cold regions is how quiet everything feels. There's a kind of steady silence that doesn't come from emptiness, but from the way the cold slows motion. You can imagine yourself there for a moment. Not as a diver, because no human could comfortably swim in water that cold without serious equipment, but as a drifting observer, moving along with the swell. The water feels thicker than the kind you know, heavier, almost syrupy in its resistance. Every creature you see seems to yield to that slowness. Even the smallest movements look measured. And this pace is not a disadvantage. It's the rhythm that allows their bodies to grow so large. Nothing rushes. Nothing darts unless absolutely necessary. Even predators conserve their motions. It's in this steady freeze that some of the giants begin to appear. A massive jellyfish drifting with tentacles trailing behind it like delicate threads, each one longer than it looks at first glance. A huge amphipod skittering across the seafloor, its size far beyond what you'd expect if you've only ever seen its warm water relatives. An enormous sea spider stretching its legs across a distance that almost looks exaggerated until you remember where you are. Then a shadow that isn't a rock at all but a gigantic isopod, its segmented shell reflecting faint patterns of dim blue light as it lifts itself over the sediment. Creatures that in warmer seas remain small enough to ignore suddenly become animals with presence. In these waters, even the simplest shapes seem enlarged. Worms become lengthy ribbons that twist across the seabed. Sea stars grow broad, thick arms capable of covering almost an entire rock with a single stretch. Sponges rise like towers instead of tiny patches. Everything seems to take advantage of the conditions and claim more space for itself. It's not a world of miniature, fragile life. It's a world of slow-building enormity. And the cold, far from hindering it, is what makes it possible. As we drift deeper into this freeze, the sheer scale of some creatures becomes more apparent. One of the most fascinating examples is the Antarctic isopod, a relative of the tiny roly-polies that you can find under rocks in your backyard. In warm waters or on land, they're only a few centimetres long, but in the cold waters around Antarctica, their close relatives can grow as large as dinner plates, with bodies strong enough to withstand crushing pressure and temperatures that rarely rise above freezing. The jump in size isn't a trick of perspective. It's real and it's dramatic. The cold environment slows their metabolism so much that they can survive with a surprisingly low level of energy intake, which frees them to invest in growth rather than constant activity. Nearby, another oversized creature moves across the ocean floor, the giant sea spider, an animal that sounds like it must be fictional until you see its proportions. Its legs spread out with a reach that seems almost unsettling by comparison to the tiny tropical versions. Its body, however, remains relatively small, almost as if all of its effort has gone into extending those long, spindly limbs that help it walk across the deep sea floor. Those legs aren't grown for intimidation. They're grown because the cold water allows for high oxygen availability, and those limbs give it more surface area to absorb that oxygen. It's a practical adaptation, not a dramatic one. And yet the result is undeniably dramatic to anyone encountering it for the first time. There are other giants drifting here too. Large amphipods, those shrimp-like creatures that are usually small enough to barely notice, reach sizes that seem almost comical. Some grow large enough that if you held one in your hand, it would fill your palm and then some. They dart with a sudden burst of motion that briefly disrupts the calm of the surrounding water before settling again. The cold benefits them in several ways: more oxygen, slower metabolism, and the stability of the deep-sea environment. They don't need to stay small and agile to escape predators that rely on quick chases. Predators here are patient. They ambush, they drift, they move with the same slowness as everything else. And once you understand that, it becomes easier to see why the giants here look the way they do. A giant worm stretching meters across the seafloor isn't a threat. It's simply taking advantage of the space and the steady environment. A massive sea cucumber, wide as a barrel and moving with an almost lazy wobble, isn't odd here. It simply evolved to store energy for long seasonal periods when food drifts down in pulses rather than steady streams. Even the filter feeders take on impressive sizes, using large bodies to collect more nutrients from the slow-moving water. One of the most awe-inspiring animals in these cold waters is the colossal squid, and though its name has become familiar through documentaries and museum exhibits, the actual creature remains far more impressive in reality than any drawing or description can capture. Unlike the smaller squids found in warm seas, it has evolved in conditions that allow it to grow far larger, with mantle lengths stretching several meters and eyes that rank among the largest in the animal kingdom. Its world is cold and dark, and in that cold and dark its enormous size gives it power and endurance. It does not race after its prey, it waits, it hovers. It uses slow, precise movements that save energy, while allowing it to stretch its body to astonishing proportions over a long lifespan. But we haven't even reached the largest of the cold water giants yet. That position belongs to the blue whale, the most massive creature ever known to live on this planet. And while blue whales travel through multiple regions, including warmer ones, their feeding grounds, the places where they depend on the greatest amount of energy, are in cold waters rich with krill. These tiny shrimp-like creatures gather in enormous swarms in the frigid oceans, creating a reliable and dense source of food that allows a blue whale to maintain its immense size. Without those cold water ecosystems, the blue whale could not grow to the scale it does. Its very existence as the planet's largest animal is tied to the productivity and stability of freezing waters. The cold seas are not simply places where giants live, they're places where giants are made. The environment sets the tempo and the creatures follow it. Their bodies reflect the slow pace, the stability, and the abundance of oxygen that cold temperatures provide. Even predators here often become larger, not because size grants them speed, but because size gives them endurance. In cold waters, endurance matters more than agility. A larger predator can wait longer, move steadily, and cover greater distances with less energy expenditure. It's a curious reversal of what we see in warm water ecosystems. In tropical regions, small and fast is often best. In the cold, big and slow wins without question. Imagine watching a massive Arctic jellyfish drifting through the deep, its bell pulsating with a steady motion. Each pulse looks unhurried, as if the animal has learned that speed is not necessary. Its tentacles spread out into the water, covering a wide area that allows it to capture prey with minimal effort. It is not in a rush, because nothing around it is. Even the currents themselves move with a thick, deliberate feel, carrying nutrients that support the jellyfish's growth over many seasons. The cold gives it longevity and a stability that warm waters rarely provide. If we continue wandering through these regions, we find that this pattern repeats itself endlessly. Large snails with heavy shells, thick-bodied fish with slow, wide strokes of their fins, spider crabs with legs that seem to stretch out farther than the eye expects. Even plankton species grow larger here, filling the water with drifting clouds of microscopic organisms that have taken advantage of the cold to expand slightly beyond the sizes found elsewhere. The entire food chain stretches upward in size, from the smallest participants to the largest, and that shift affects every predator, every scavenger, and every drifting feeder that moves through the cold. But this isn't just about bodies increasing in size for no reason. It's about the way cold alters the entire structure of an ecosystem. The nutrients behave differently, the currents behave differently, the cycles of life and reproduction behave differently. Many cold water species live longer lives because the slow metabolism helps them avoid the wear and tear of rapid energy use. A creature that lives longer has more time to grow. And because growth never rushes in these waters, size becomes a gradual achievement rather than a quick sprint. It's interesting to think about how the same animal might look if you simply changed its environment. A familiar species placed in colder waters often grows larger. The same species placed in warmer waters remains smaller. This pattern isn't limited to the ocean. It appears in many kinds of environments across the world. Scientists call it a rule, an observation that cold regions tend to produce larger-bodied animals. But the ocean offers the most dramatic examples, especially in the deep and in the polar seas. Here, the rule becomes more like a recurring theme that defines entire groups of organisms. As we continue drifting through this icy environment, it becomes clear that the cold is not a barrier to life, but a sculptor of it. The giants that live here are not exaggerations or anomalies. They are the natural outcome of long stretches of time spent in a place where size provides stability, where energy can be conserved through slowness, and where oxygen allows cells to perform efficiently. The cold invites growth, not by speeding it up, but by letting it unfold at a pace that leads steadily toward immensity. And as we follow these drifting giants through the deep freeze, we begin to see how the unique physics of cold water allow them to thrive in ways that warm water species cannot. There is a logic to their largeness. Every adaptation makes sense when viewed through the lens of slow metabolism, abundant oxygen, stable pressure, and the need for endurance over speed. The cold shapes life gently but with a firm hand, guiding it toward forms that look almost exaggerated but are perfectly suited for the environment. As we continue deeper into this story, we'll start to look more closely at the biological reasons behind this phenomenon, exploring how the cold changes internal processes and how these changes ripple outward to shape the giants we see drifting through these frozen waters. The freeze is not the end of life, but the beginning of a different kind of growth, and understanding that takes us further into the workings of life in the cold than simple observation can show. When we move from the world of drifting giants to the quiet forces that allow them to exist at all, the picture becomes clearer in a way that feels both simple and strangely powerful. Life in the cold isn't just shaped by evolution in the broad sense, it's sculpted by physical laws that behave differently here than they do in warmer places. Everything we've seen so far, the slow movements, the heavy bodies, the large shapes, is rooted in the way cold water changes the rules. Not in a mysterious or magical way, but in a steady mechanical way that affects every cell, every breath, every molecule of the creatures living there. The physics of cold water is the quiet architect building these immense bodies piece by piece over time. Before diving too deep into the mechanics, it helps to remember what cold actually means for molecules. In warmer temperatures, molecules move quickly. They bounce, they collide, they zip around each other in constant motion. The energy feels jittery, almost restless. In colder temperatures, the opposite happens. Molecules slow down, their movement becomes more restrained. The energy they carry drops, and the water around them becomes denser and heavier. This slower dance sets the entire stage for life in cold oceans. It influences how fast chemical reactions happen, how much oxygen dissolves in the water, how nutrient cycles behave, and how energy flows from one organism to the next. One of the most important pieces of this puzzle is oxygen. Cold water can hold far more oxygen than warm water. This isn't a gentle difference, it's a significant one, large enough to completely transform the possibilities available to living things. Oxygen is the fuel of most life on Earth. Creatures need it to break down food, store energy, and power every cell in their bodies. In warm water, oxygen escapes easily. It slips into the air, leaving the water with much smaller reserves. In cold water, oxygen stays dissolved. It saturates the environment, making it easier for animals to breathe, especially those that rely on passive diffusion instead of active lungs or gills. This abundance of oxygen is one of the main reasons cold water animals can grow so large. When oxygen is plentiful, cells can function efficiently even in large bodies. They can grow, repair, and operate without struggling for breath. Warm water creatures often face limitations on size, not because they don't have the genetic potential to grow, but because their environment restricts how much oxygen their tissues can access. In cold water, this limitation eases. It opens the door for bodies that stretch far beyond what would be possible in warmer regions. But oxygen isn't the only piece of the story. The cold also slows metabolism. In warm environments, animals burn through energy quickly. They move fast, digest fast, breathe fast, and live fast. Their bodies are constantly working to keep up with the demands of warm water survival. This speed makes them small because small bodies heat and cool quickly, move efficiently, and require less energy overall. In the cold, however, metabolism drops. Everything takes longer. Digestion slows. Growth becomes a measured process rather than a rapid sprint. Movement becomes steady instead of abrupt. And with that slowness comes an interesting advantage. Creatures don't need to eat as often, and they can stretch small amounts of food across long spans of time. That stability allows them to build more mass over the years. Slow metabolism also reduces the wear and tear that comes from rapid movement. Tissues last longer. Lifespans extend. A creature that lives longer has more time to grow. When you combine long life, slow metabolism, and abundant oxygen, the outcome is almost inevitable. Big bodies built with patience rather than urgency. Pressure also plays a role here. In deep, cold waters, pressure increases with every meter of depth. At thousands of meters below the surface, the weight of the water above becomes immense. Warm water environments closer to the surface never reach those levels of pressure, so the creatures living there rarely grow structures that can withstand such force. In the deep cold, however, bodies must be built to endure it. These adaptations reinforce strength and stability. Many deep-sea animals develop thick shells, sturdy exoskeletons, dense muscles, or flexible, pressure-tolerant tissues that allow them to survive in conditions that would crush most warm water species. And once you've developed structural features that are robust enough to withstand the pressure, growing larger often becomes a natural consequence rather than an additional challenge. Another subtle but important factor is the thickness or viscosity of cold water. When water cools, it becomes slightly thicker. The particles in it move more slowly and hold together more tightly. This thickness affects how creatures move. For a small creature, this viscosity creates resistance that can be difficult to overcome. Staying small and active in cold water requires more effort than in warm water. Larger animals, on the other hand, handle this viscosity more easily. Their bodies push through the resistance without being hindered by it. Their size becomes an advantage instead of a burden. When moving through cold water, a larger body can glide more steadily and more efficiently, while a tiny one struggles. Even food behaves differently in cold regions. In warm waters, nutrients are often spread thin because surface layers stratify, preventing deep, nutrient-rich water from rising. In cold waters, stratification doesn't happen the same way. Seasonal cycles stir the water, ice melts, sinks, and mixes nutrients vertically. The result is a richer, more reliable supply of food that supports larger creatures, particularly filter feeders and slow-moving predators. Food arrives in pulses rather than continuous streams, which encourages species to store energy in large bodies and wait for the next productive season. To understand how all these factors combine, imagine a creature living in cold water. It breathes easily because oxygen is abundant. It moves with slow, steady motions because the cold has reduced its metabolic needs. It can store energy in a large body because food arrives in seasonal waves that it must endure between bursts of abundance. It adopts a form that can withstand the pressure of deep water. And because the environment doesn't pressure it to move quickly, it shifts its evolutionary focus from speed to endurance. The body grows, not in a frantic way, but gradually year after year. This physics-driven growth is especially noticeable in invertebrates. Many of them rely on simple respiratory processes, diffusion across surfaces, or gills that function better when oxygen is plentiful. When oxygen saturates the water, these systems become much more effective. Their bodies don't need to remain small to ensure enough oxygen reaches their tissues. They can safely expand. The giant sea spider is a clear example of this. Its long legs massively increase its surface area for oxygen absorption. Without cold water providing high oxygen levels, those legs couldn't support such a sprawling body. The environment makes the anatomy possible. Similarly, amphipods and isopods expand dramatically in cold regions because their oxygen intake scales well with larger size when the environment cooperates. In warm waters, oxygen limitations cap their size. They cannot grow large without suffocating. In the cold, this limitation disappears, and their bodies grow until the other environmental constraints define the upper limit. It's not just oxygen that allows this. Cold slows decay as well. Organic matter breaks down more slowly in frigid temperatures, which means that food sources remain available longer. In warm regions, dead plants or animals decompose quickly, with bacteria and scavengers breaking them apart rapidly. In cold waters, decomposition takes far longer. A fallen organism can remain intact long enough to become a reliable source of nutrients for creatures that find it. Slow decay supports larger scavengers because it gives them time to locate and consume the remains. Chemical reactions inside the bodies of cold water creatures also slow down. These reactions control everything from muscle contractions to nerve signals, growth processes, digestion, and cellular repair. When temperatures drop, these reactions don't stop. They simply proceed at a different pace. Cold water species often develop specialized enzymes or proteins that function well at low temperatures, allowing their bodies to operate without freezing. These adaptations make their internal processes both stable and predictable. Stability encourages endurance, and endurance again encourages size. In a warm environment, fast chemical reactions drive creatures toward quick life cycles. They reproduce rapidly and grow quickly, but rarely reach massive sizes because their bodies spend so much energy staying alive at high speeds. In the cold, slower reactions mean slower growth, but also longer growth. Over decades, this steady pace accumulates into remarkable size. Another part of the physics of cold environments is buoyancy. Water density increases as temperature drops. This increased density provides more natural lift to bodies moving through the water. Large animals require less energy to remain suspended or to rise and fall within the water column. Their size does not weigh them down the way it might in warmer, less dense water. Buoyancy helps support large bodies and makes it easier for them to drift, hover, ambush, or filter feed with little energy lost. Even predation dynamics shift in cold water. Fast chases become less practical. Sudden escapes become less common. Instead, predators rely on stealth, patience, and endurance. These strategies reward size. A larger predator can wait longer for prey without burning excessive energy. A larger prey animal can resist a single attack or survive longer between feeding opportunities. Both sides of this interaction benefit from size in different ways. The physics of the environment shapes the behavior of both predator and prey, nudging both toward greater scale. It's also worth noting that cold water animals often exhibit thicker insulation. This isn't just for warmth, but also for energy storage. Fat stores accumulate because the environment demands they be prepared for long periods with limited food availability. These fat reserves add mass, contributing to the animal's overall size. But rather than being a burden, this mass is a benefit. It keeps them warm, stores energy, improves buoyancy in some cases, and serves as protection from the cold. All these physical realities create a kind of ongoing negotiation between organisms and their environment. Every adaptation is a response to the physics of cold. As creatures adapt to survive, their bodies change shape, scale, and capability. Over millions of years, these adjustments become the default form. The giants of cold waters aren't exceptional in their own world. They are the natural answer to a long list of physical pressures and advantages that the cold provides. If we step back and look at these cold water ecosystems as a whole, they begin to resemble a slow-moving engine. The physics provides the structure, the chemistry provides the pace, the biology follows. The engine turns steadily, predictably, and quietly. It doesn't produce many flashes of speed or sudden changes. It produces endurance, longevity, and mass. The cold nurtures size by making it easier to maintain large bodies and harder to maintain small ones. Over time, this imbalance shifts the entire ecosystem upward in scale. As we stay with this idea, the connection between physics and biology becomes more direct. The cold doesn't just create giants, it requires them. Small creatures struggle more with cold environments because their bodies lose heat quickly. Their surface area is too high relative to volume, and their internal processes slow beyond functional levels. Larger bodies conserve heat better, even in creatures that don't regulate their temperature. They have more reserves, more structure, more oxygen uptake, and more stability. The cold rewards those traits again and again until the giants become the normal residents of these regions. And as we move on from this set of physical explanations, the story naturally leads into how these forces shape evolution itself. Not just the moment-to-moment survival strategies, but the long arcs of change across generations. The cold doesn't simply freeze time, it stretches it in a way that guides species toward forms that would be improbable elsewhere. And that takes us deeper into the evolutionary patterns that have shaped these enormous animals over millions of years, showing how adaptation and time work together to create the vast forms drifting through the cold. When we focus on the cold oceans and try to understand why so many of their creatures grow to such unusual sizes, one detail keeps returning in almost every explanation. Cold water holds an enormous amount of oxygen, much more than warm water ever can, and that extra oxygen changes everything. It doesn't just help animals breathe more easily, it reshapes their entire physiology. It determines how large they can grow, how fast they move, how long they survive, and even how they interact with their surroundings. The giants drifting in these waters don't simply tolerate cold. They thrive because the cold carries the breath they need in abundance. Oxygen is one of the most basic requirements for life as we know it. For animals, especially large ones, it's the fuel that powers every cell. Without enough oxygen, a creature's body reaches a hard limit. Muscles can't expand further, organs can't support more tissue, and metabolism suffers. Warm water animals often push against those limits. They must stay small, quick, and efficient because oxygen is harder to come by. The heat makes the molecules in the water move rapidly, leaving little room for dissolved gases. As temperatures rise, oxygen slips out of the water and into the air. Warm tropical waters may look vibrant on the surface, but they often hold less of the fundamental ingredient that supports large bodies. Cold water behaves differently. When temperatures drop, oxygen dissolves easily and stays dissolved. It doesn't escape, it saturates the environment. Even a quick comparison shows how dramatic this difference is. Near freezing water can hold almost twice as much oxygen as warm equatorial seas. That extra oxygen doesn't just float around unused, every creature in the region takes advantage of it. To understand how important this is, imagine an animal's body from inside out. In the simplest terms, every cell inside that body needs oxygen to function. Not just for breathing in the everyday sense, but to break down food, repair tissues, produce energy, and grow. The bigger the body, the more cells it contains, and the more cells it contains, the more oxygen those cells require. Without a sufficient supply, large bodies become unsustainable. They begin to collapse under their own demands. Warm water species find their maximum size capped by this limitation. Cold water species, on the other hand, live in an environment where the oxygen supply is rarely the limiting factor. Their bodies can expand without threatening their own survival. This becomes especially important for animals that rely on simple breathing structures. Many of the giants in cold waters don't have lungs or complex gills. Some absorb oxygen directly through their skin. Others use surfaces lined with thin membranes. These methods are efficient only when oxygen levels are high. Put those same species in warm water and they quickly shrink or struggle. Place them in cold water rich with oxygen, and their size increases generation after generation. The giant sea spider is one of the clearest examples. Its body seems almost disproportionate at first. It has a small central core and extremely long legs. Those legs aren't just for walking across the seafloor. They act as surfaces for oxygen absorption. The creature doesn't use lungs or traditional gills. Instead, it relies on the oxygen that diffuses across the membranes in those legs. In warm water, that system would fail. In cold water, where oxygen's plentiful, those long legs become a huge advantage. They allow the animal to grow far larger than its warm water relatives, with enough oxygen reaching every part of its body. The same principle applies to Antarctic amphipods, deep-sea worms, enormous isopods, and other invertebrates that balloon in size in cold regions. Their bodies are built for simplicity, and simplicity thrives when oxygen is everywhere. These animals don't need complicated machinery to move oxygen around. The environment delivers it directly to them. They can grow larger without redesigning their internal systems. It's almost as if the cold ocean gives them a free pass, removing the usual limits placed on small-bodied creatures. Even animals with more advanced respiratory systems benefit from the oxygen-rich water. Fish living in cold seas tend to have larger gills relative to their body size. They take in more oxygen with each passing moment. Their muscles can do more work with less effort. Their organs can support greater mass. The abundance of oxygen reduces the strain on every part of their anatomy. Instead of operating at the edge of their limits, they operate comfortably below those limits. That comfort gives them room to grow. When we extend this idea to some of the largest animals ever known, the pattern becomes even more striking. The blue whale, as enormous as it is, depends on cold waters during its feeding season for a reason. The prey it feeds on, krill, requires oxygen-rich conditions to exist in the vast swarms that sustain whale populations. Krill themselves benefit from cold, oxygenated water. They grow in extraordinary numbers, forming dense masses that only exist in regions where the environment supports them. Without those swarms, the energy required to feed a blue whale would be impossible to gather. So the whale's size is not just linked to its own biology, but to the biology of the creatures beneath it, all of them connected to the cold's ability to hold oxygen. Oxygen also governs how active these large animals can be. Warm water species burn energy quickly because their metabolism runs faster. With less oxygen available, they must pace themselves carefully. Their bodies can't afford long bursts of activity without risking exhaustion. Cold water animals don't face that same constraint. A large creature in an oxygen-rich environment can afford long, slow movements that barely tax its energy reserves. Its muscles aren't starved. Its organs aren't straining. It has room for endurance. Consider the colossal squid. It lives in waters where oxygen is plentiful, but food is not. It cannot afford to chase prey in quick, desperate bursts. Instead, it relies on slow, controlled motions, hovering quietly until the right moment. That approach is only possible because the cold water provides a steady supply of oxygen that keeps its enormous muscles ready without burning through energy too quickly. The oxygen gives it power without forcing speed, power without the constant urgency seen in warm water predators. Cold water fish show similar patterns. Many of them develop large, slow-moving bodies that conserve energy while remaining capable of sudden bursts when needed. Their muscles, supported by the readily available oxygen, perform reliably in low temperatures. They can cruise long distances without tiring. They can sit still for hours without losing strength. This endurance is a direct consequence of how their environment feeds oxygen into their bodies. Even filter feeders benefit from this. Cold water sponges, sea squirts, and other stationary organisms often grow large because their bodies can process nutrients efficiently when oxygen's abundant. Their cells don't choke or fall behind. Their structures expand over time because the basic functions that keep them alive operate smoothly in the cold. Oxygen doesn't speed up their lives. It keeps their lives stable, which is even more valuable in an environment where food arrives in seasonal cycles. One of the more surprising details about oxygen-rich waters is how much they support long lifespans. Many of the giants in these cold regions live far longer than their warm water counterparts. This is partly due to slow metabolism, but oxygen contributes just as much. When oxygen supply remains high throughout an animal's life, it reduces the stress on its cells. Damage accumulates more slowly. Repair processes work more efficiently. Longevity becomes possible not because the animals have special genes, but because the environment gives their bodies what they need for decades. Take the Greenland shark, for example. It lives in some of the coldest waters on Earth, and grows at a pace so slow it's almost hard to comprehend. Its body takes advantage of every ounce of oxygen the water offers, moving through life at a steady, unhurried rate. Scientists estimate that some individuals live for centuries. The shark's immense size doesn't come from rapid growth, but from consistent oxygen-supported growth that continues for a lifetime far longer than most animals ever experience. Oxygen-rich waters also influence how energy flows through entire ecosystems. In warm waters, energy moves quickly but chaotically. Food appears in bursts, disappears fast, and forces species to adapt to sharp changes. In cold waters, oxygen helps stabilize everything. Producers grow in steady patterns. Consumers rely on predictable oxygen levels. Predators and prey find rhythms that don't fluctuate wildly. This stability supports large animals because it gives them predictable conditions. They don't need to shrink in response to sudden environmental shortages. Their world is consistent enough to allow long-term investment in growth. When you look closely at all these pieces, a clear pattern emerges. Oxygen is one of the main reasons the giants exist. They aren't anomalies. They aren't lucky. They are the natural outcome of an environment that supplies them with more breath than they strictly need. That surplus allows them to build and maintain massive bodies that would collapse in any other setting. The breath of the cold doesn't simply support life. It reshapes it. It becomes the quiet force that powers animals large enough to appear almost unreal. It fills their muscles, strengthens their organs, stabilizes their metabolism, and fuels their slow, deliberate movements through the water. Without it, the cold would still slow things down, but size would remain limited. With it, the cold becomes a place where life can stretch out and occupy a scale that feels almost impossible in warmer regions. As we keep following this story, oxygen becomes only one piece of the larger pattern that shapes immense creatures in freezing waters. There are still the deep metabolic changes, the strange efficiencies that cold offers, and the evolutionary pathways that have taken these animals from ordinary beginnings to extraordinary forms. The breath of the cold gives them the potential. The next steps reveal how they use it to become the giants drifting through these frigid seas. If oxygen gives cold water creatures the breath they need to grow large, then the pace at which they use that breath shapes what they become. A slow metabolism might sound like a limitation at first. In everyday life, we associate slowness with inefficiency, with heaviness, with inactivity. But in the cold oceans, that slowness becomes something entirely different. It becomes a strategy, a stabilizing force, and ultimately one of the most important reasons creatures here reach such impressive sizes. The cold dampens everything: movement, growth, digestion, chemical reactions, and the speed at which bodies wear down. Instead of being a burden, that dampening turns into a path toward immensity. Most animals in warmer waters live fast. They have no choice. The heat speeds up every process inside them. Their cells burn energy quickly. Their muscles need constant fuel. Their organs must work continuously to keep up with the pace set by the environment. It creates a world where life cycles rush by. Many warm water species grow quickly, reproduce quickly, and die quickly. There's little time to accumulate mass, rebuild tissue slowly, or maintain a large body over many years. Their metabolism sets a cap on what is possible. In cold waters, the opposite takes place. Everything slows down, not to a stop but to a steady rhythm that doesn't demand constant urgency. Slow metabolism means the body uses less energy to stay alive. It reduces the strain on organs, muscles and tissues. It creates room for the kind of long-term growth that leads to large sizes. Instead of racing through life, creatures here move through it with patience. Their bodies grow over long periods, often years or decades, not because they are trying to become large as fast as possible, but because the environment allows them to accumulate mass steadily without collapsing under metabolic demands. When a creature's metabolism slows, several important things happen inside its body. First, the rate at which cells divide decreases. That might sound like it would prevent growth, but what it really prevents is damage. Fast-growing animals often accumulate errors in their cells because their bodies rush to replace or repair tissues. Slow growth avoids this. It produces stronger, healthier structures. Bones strengthen, muscles thicken, shells form more evenly. Tissues build themselves in a way that supports long-term maintenance rather than short-term survival. The second thing that happens is a drop in the amount of energy required to stay alive. When metabolism is slow, an animal can go longer without food. It can survive lean periods. It can store energy more effectively. All of that encourages larger bodies because a larger body can hold more stored energy. Instead of being a burden, size becomes an advantage that allows survival across long seasons when food arrives only in bursts. This pattern shows up clearly in many cold water species. Sea cucumbers in deep, cold regions grow far larger than their warm water relatives because their slow metabolism allows them to store nutrients over long periods. Giant isopods become huge because their metabolism lets them endure months without a meal. When they finally feed, they store the energy in their broad bodies. The cold slows everything around them, so they aren't forced to burn those reserves quickly. Slow metabolism also reshapes how predators and prey interact. In warm waters, speed is almost always essential. Predators chase down prey with rapid bursts. Prey escape with quick maneuvers. Both sides burn through energy rapidly. Both sides stay relatively small because small bodies move efficiently during rapid action. In cold waters, slow metabolism affects every level of this relationship. Predators do not rely on speed. They rely on patience and endurance. Prey don't race away, they conserve energy by moving minimally. In this calmer dynamic, large bodies make sense. A slow-moving predator with a large body can wait for hours or days without tiring. A slow-moving prey animal with a large body has more energy stored and is less vulnerable to sudden attack. The entire system shifts towards stillness, and that stillness favours size. Another advantage of slow metabolism is reduced cellular damage. In warm waters, animals generate more free radicals, unstable molecules that damage cells, simply because their metabolism runs fast. Over time, that damage limits lifespan and growth. In cold waters, slower metabolism generates fewer of these harmful molecules. Cells stay healthier, tissues last longer. If damage does occur, the slower pace allows more careful repair. A long-lived creature with steady repair processes can grow to impressive sizes without the deterioration that would limit similar growth in warm regions. This is part of why some of the longest-lived animals on the planet come from cold waters. The Greenland shark lives for centuries, growing slowly, using energy sparingly, and letting its body accumulate mass at a pace that barely seems to move from year to year. The Antarctic sponge grows so slowly that some individuals alive today may have started growing before major human civilizations existed. These creatures don't simply become large because they grow quickly. They become large because they grow for a very, very long time. Slow metabolism also changes how animals eat and digest food. In warm waters, digestion is fast because the chemical reactions involved move quickly. Animals must eat often to maintain their pace. In cold waters, digestion takes far longer. Food moves slowly through the body. Nutrients are absorbed steadily. Because digestion is slow, animals do not need to eat as frequently. This encourages growth in a different way. A creature that doesn't need to constantly search for food can invest its energy into building and maintaining a larger body. The cold removes the pressure to stay small and agile in search of constant meals. Consider the giant sea anemones found in cold regions. In warm waters, anemones tend to remain small because they catch small prey and digest it rapidly. In cold waters, the process slows dramatically. A large anemone can catch a substantial meal, digest it over a long period, and store that energy as body mass. The slow digestive process becomes a pathway toward increased size. Slow metabolism also affects how creatures reproduce. Warm water species often invest energy into producing many offspring quickly, because lifespan is short and the environment is unpredictable. Cold water species tend to produce fewer offspring, but they invest more energy in each one. Their slow metabolism allows them to preserve enough energy reserves to nurture larger eggs or developing young. When young animals start life with larger bodies, they're more likely to survive in environments where the pace is slow, but the conditions can be harsh. Over generations, this reproductive pattern pushes species toward larger average sizes. Another detail to consider is that slow metabolism makes animals more tolerant of the deep ocean's extreme pressures. At great depths, pressure can be thousands of times higher than at the surface. Rapid metabolic processes would struggle here because chemical reactions become harder under pressure. Slow reactions, however, continue with fewer disruptions. This makes cold, deep environments particularly suited to creatures that move slowly and grow steadily. Many of them evolve at these depths where cold and pressure combine to create some of the most stable conditions on the planet. In that stability, slow metabolism becomes not a disadvantage but the best possible approach to life. Even animals that migrate through cold waters take advantage of slow metabolism. Some fish and marine mammals enter cold regions to feed, rest, or grow. During these periods, their metabolism shifts slightly to match the environment, allowing them to conserve energy and recover from high-energy activities like breeding or migrating. The cold becomes a place where they can rebuild, replenish, and gain mass before returning to warmer waters. For species like the blue whale, these cycles shape their entire existence. Slow metabolism also reduces the need for constant movement. In warm waters, animals must often stay active simply to find enough food or oxygen. In cold waters, with slow metabolism and abundant oxygen, animals can remain still for longer periods. They aren't forced into a lifestyle of near-constant motion. A creature that spends more time resting and less time searching for food saves enormous amounts of energy. That energy can be channeled into growth, fat storage, thickening tissues, and building the large structures that define cold water giants. One of the most consistent patterns among cold water giants is how their bodies distribute energy. In warm waters, energy must be used quickly to maintain pace. In cold waters, energy accumulates slowly but reliably. Fat deposits grow, muscles thicken, exoskeletons strengthen, shells become heavier. These structures are expensive to build in metabolic terms, but slow metabolism allows that cost to spread across a long timeline. The result is a body that appears oversized compared to warm water relatives but is perfectly suited for its home environment. This slow-building approach to life also reduces competition. In warmer waters, competition for food can be intense. Many species rush to exploit resources the moment they become available. In cold waters, food arrives slowly and unpredictably, and slow metabolism makes creatures less dependent on winning these sudden races. Their energy needs are lower. Their bodies are built for endurance. They can wait out lean times that would devastate smaller, faster species. Because they don't have to compete as fiercely, they can grow larger without that growth turning into a liability. Longevity plays a major role as well. A creature with a slow metabolism often lives long enough to grow to sizes that warm water creatures never reach. When growth is spread over decades, the numbers add up. A fish that adds only a tiny amount of mass each year can still become enormous if it lives long enough. A sponge with a glacial growth rate can reach monumental size simply by persisting long enough. In these environments, the phrase slow and steady becomes more than a simple saying. It becomes the fundamental blueprint for survival and growth. Slow metabolism also influences how animals respond to injury or environmental stress. Warm water animals must devote energy quickly to repair and recovery. Cold water animals, by living on a slower schedule, often spread these repair processes over longer periods. Instead of rushing through healing, they rebuild tissues gradually. This approach reduces mistakes and improves the strength of repaired structures. A body that keeps itself in good condition for decades or centuries has more time to grow large without falling apart under its own weight. If we step back and look at all these patterns, a picture forms of an environment where slow metabolism is not a handicap but a foundation. It gives creatures time that warmer regions simply don't offer. It reduces the urgency of life. It allows bodies to grow, strengthen, store and endure. Each extra year or decade adds another layer to the creature's size, another opportunity to expand into the environment that has gently shaped it. And as this slow, patient growth unfolds, cold water animals begin to resemble something almost out of scale with their relatives in other regions. They don't look oversized because they rushed. They look oversized because nothing ever forced them to shrink or limit themselves. The cold gives them room, time gives them form, metabolism gives them the pace needed to become immense. As we move forward, this slow metabolic rhythm leads naturally into the broader evolutionary patterns that have driven cold water gigantism for millions of years. The environment sets the pace, but evolution decides how that pace gets written into the bodies of the creatures drifting through these freezing seas. When we try to understand why the cold shapes creatures into larger forms, it helps to step back and consider the broad, long-term patterns that biologists have observed all over the world. For centuries, naturalists noticed something strange. Animals living closer to the poles often grew larger than animals of the same species living nearer the equator. Birds, mammals, reptiles, invertebrates, across groups, the same trend appeared. Even long before scientists understood the mechanics behind it, they recognized that cold regions seemed to encourage bigger bodies. This recurring pattern became known as the polar rule, or more formally as Bergmann's rule. It doesn't explain everything about cold water giants, but it provides an important starting point for understanding why freezing environments amplify the body in such a consistent and predictable way. The polar rule isn't just a vague observation. It shows up repeatedly in real, measurable examples. Bears in the far north grow larger than their warmer cousins. Wolves in colder habitats are heavier than wolves closer to the tropics. Many cold water fish grow larger than similar species in mild regions. Even among humans, populations adapted to colder climates historically average larger body masses than those from warmer ones. The rule isn't absolute. There are exceptions, and not every species follows it perfectly. But the trend holds strongly enough that it has become one of the most dependable patterns in ecology. To understand why, we need to look at how bodies lose heat. Every animal gives off warmth. It's an unavoidable consequence of being alive. The key factor is surface area. A small body has a large surface area compared to its volume. A large body has a smaller surface area relative to the mass inside it. The smaller the surface area, the slower the heat escapes. In warm environments, animals don't need to conserve heat. They often do the opposite. They try to get rid of excess heat so they don't overheat. Small bodies help with that. In cold environments, conserving heat becomes essential. Large bodies hold warmth better. They lose heat more slowly. They stay functional longer in frigid temperatures. This heat conservation effect explains much of the polar rule, but when we bring it into the ocean, the pattern intensifies. Water pulls heat from a body much faster than air ever could. Even mildly cold water drains warmth at a pace that would shock most land animals. In the polar seas, the danger isn't just cold air, it's a medium that strips heat continuously. A larger body becomes an efficient way to resist that drain. It gives the creature more internal volume to generate heat and less surface area to lose it. For warm-blooded animals like whales, seals, and penguins, this relationship is clear. Their immense size isn't merely a product of evolution's creativity. It's a survival tool perfectly matched to the physics of their habitat. But the polar rule doesn't stop at warm-blooded creatures. It influences cold-blooded animals too, in ways that at first seem contradictory. Cold-blooded creatures don't generate their own heat. They rely on the environment to warm their bodies. You might expect them to stay small in cold places because large bodies warm more slowly. Yet many of them also become giants in cold waters. The explanation for them lies not in heat retention, but in other advantages that large bodies offer, advantages that become even more useful in cold oceans than on cold land. One of those advantages is energy storage. A larger body can store more fat, more nutrients, more reserves needed to survive periods when food is scarce. In the polar regions, food often comes in pulses. During certain seasons, the waters explode with life. Plankton blooms, krill swarms, nutrient upwellings. But in other seasons, food nearly vanishes. A small animal with a fast metabolism would struggle. A large animal with stored energy can survive the lean months without constant feeding. Over generations, this dynamic encourages the evolution of larger bodies, because creatures with more reserves survive the long winters and reproduce more successfully. Another advantage involves pressure and mobility. In the deep ocean, cold waters extend downward into regions of crushing pressure. Small creatures often struggle to move efficiently through these depths because their bodies lack the momentum to glide or drift without constant effort. Larger bodies experience drag differently. They move with more fluidity through thick, cold water. Their momentum carries them farther. Their size becomes a stabilizing force, helping them navigate environments that would exhaust smaller animals. Then there's reproductive output. Large bodies often produce larger offspring or more resilient eggs. In cold environments where young animals face harsh conditions from the moment they emerge, size becomes an important safeguard. A slightly larger egg might contain enough nutrients to sustain a developing embryo longer. A slightly larger juvenile might withstand the cold better or survive longer between meals. Over time, the polar rule influences not only adult bodies, but the early stages of life as well. When we apply all these forces, heat conservation, energy storage, movement efficiency, reproductive survival, and slow metabolism, the pattern becomes clear. Cold doesn't automatically cause animals to grow larger. Cold creates a set of conditions where larger animals survive more easily. Evolution takes care of the rest. This pattern becomes even more striking when we examine how entire food webs shift in cold regions. In warm waters, energy flows quickly. Producers like algae and small plants grow fast. Herbivores eat quickly. Predators chase prey at high speed. Everything moves rapidly through the ecosystem. In cold waters, the pace changes entirely. Nutrients move slowly. Algae grow in bursts related to sunlight and seasonal cycles. Animals feed at a slower pace. The energy flow becomes smoother and less frantic. When energy flows slowly, animals don't need to stay small to react quickly. They can afford to slow down, conserve energy, and let their bodies grow. This is one reason why the Antarctic Ocean supports such large populations of krill, tiny animals individually, but collectively one of the largest biomasses on the planet. Their growth is tied to cold waters, where nutrients cycle reliably through the seasons. And because there are so many of them, they support many of the largest animals in existence. The scale of life in cold regions doesn't begin with giants. It begins with rich foundational species that thrive in the cold. The giants are simply the final expression of a food web built on slow cycles and abundant oxygen. The polar rule also helps explain why cold water gigantism can occur even in groups where it might seem surprising. Sponges, for example, grow to massive sizes in polar seas. Cold slows their growth rate dramatically, but it also extends their lifespan. A sponge that grows for several hundred years can become enormous, not because it grows fast, but because it grows steadily without interruption. The cold ensures that its tissues remain stable. The problem in warmer waters is that rapid metabolic processes lead to breakdown, death, or predation long before a sponge could reach such age. Cold waters remove those barriers. Another place where the polar rule becomes clear is in crustaceans. In warm waters, crabs and shrimp tend to stay relatively small. Their bodies require large amounts of oxygen to move quickly, and warm waters simply don't hold enough oxygen to support oversized individuals. In cold waters, that limitation disappears. Oxygen saturates the environment, and slow metabolism reduces overall energy demands. Combined with the polar rule's tendency to favour mass for survival, this pushes species like Antarctic sea spiders and giant amphipods towards sizes that dwarf their tropical relatives. One interesting detail is how the polar rule interacts with surface-to-volume ratios. Even in cold waters, not every species becomes large. Tiny plankton, for example, remains small because their survival depends on drifting with currents. But many mid-sized species shift upward in size because the cold favours volume over surface area. For every increase in volume, the body gains mass and internal resources. For every increase in surface area, the body loses heat and energy. In warm waters, small bodies with large surface areas thrive because they lose heat rapidly and stay active. In cold waters, small bodies with large surface areas lose heat too quickly. Larger bodies with smaller proportional surface areas endure better. This rule even influences how bodies are shaped. In cold regions, many animals develop rounder or thicker forms. They reduce their surface area further. The result is animals that look sturdier or more robust than their tropical relatives. Their shapes reflect the environment as much as their sizes do. A rounder seal loses heat slower. A thicker fish conserves warmth more effectively. A bulky crab uses less energy to maintain its body temperature. Shape becomes part of the adaptation alongside size. One of the best examples of this is the polar bear. Although this is a land mammal, its adaptations reflect the same principles guiding marine giants. Polar bears evolved bodies that conserve heat so effectively that they often overheat rather than freeze. Their enormous size reduces heat loss. Their round, powerful forms hold warmth better than a slender body would. Although they live on ice, their entire evolutionary trajectory reflects the same rule that shapes whales, seals, and cold water fish. In the ocean, seals and whales take this to an extreme. Their bodies aren't just large, they are massive. Thick layers of fat reduce surface area heat loss, give them buoyancy and store energy. Their size allows them to maintain body heat in freezing waters, even though they lose temperature much faster in water than they would in air. Without their immense mass, these animals would not survive the polar seas. The cold demands it. Even fish that we normally think of as agile and streamlined become thicker in cold waters. Arctic cod, for example, develop bodies that store fat and resist heat loss. Their cold water relatives tend to have shorter fins, thicker bodies, and slower movements than their warm water cousins. These differences reflect millions of years of adaptation to conditions where size and mass offer the greatest advantage. When we pull all these threads together, the polar rule becomes more than a simple statement. It becomes a framework that explains why cold regions are filled with such impressive creatures. The cold does not simply allow larger bodies, it pushes species toward them. It rewards mass. It favours animals that can conserve heat, store energy, move efficiently, reproduce successfully in harsh conditions, and endure long periods of scarcity. Over countless generations, these small advantages accumulate. The creatures grow larger. Their bodies become the perfect answer to an environment shaped by cold. And as we follow this path, the question naturally extends into deeper evolutionary patterns. If cold favours larger bodies, how have these species evolved across millions of years to amplify that advantage even further? The next part of the story steps from environmental physics into evolutionary history, tracing how these giants came to be shaped by time as much as by temperature. When we descend far enough into the cold oceans, deeper than sunlight can reach, deeper than most animals from the surface could survive, we enter a world that feels almost detached from the rest of life on Earth. The abyss is not just dark. It is quiet in a way that land or shallow water can never be. The pressure becomes intense, the temperatures drop until they hover just above freezing, and everything slows into a rhythm shaped only by the steady physical realities of this place. In this vast, cold expanse, a strange pattern appears again and again. Many of the animals living here grow to sizes that seem almost exaggerated compared to their shallow water relatives. Their silhouettes drift through the dimness like shadows larger than anything we expect to find in places so hostile. Gigantism is not an oddity here. It is common. It is a repeated outcome of the conditions that define the deep. The first thing that stands out when imagining the deep sea is how little energy flows through it. There are no plants here. Photosynthesis stops at the surface the moment sunlight can no longer penetrate the water. Everything living thousands of meters down depends on the slow arrival of organic material drifting from above, often in sparse and unpredictable amounts. You might expect this food scarcity to keep animals small, fragile, and minimal, but that isn't what happens. Instead, the deep fills with creatures whose bodies are large, heavy, and often strong enough to endure pressures that would crush more delicate forms. This counterintuitive result makes sense only when we examine a few details about how these animals survive. The slow arrival of food, for example, encourages animals to store energy, and storing energy effectively requires mass. A small creature burns through its reserves quickly. A large creature can hoard energy in thick tissues, dense muscles, or fat deposits. The cold deep allows that stored energy to last longer than it ever could at the surface. Slow metabolism helps too. Many deep-sea animals move only when necessary. They drift, hover, or settle into the sediment, saving every bit of energy for rare moments when it truly matters. Over a long lifetime, sometimes decades, sometimes longer, that steady conservation of resources allows them to grow continuously, even if only a tiny amount each year. As we drift deeper into this environment in our imagination, the first giants that often come to mind are the huge squid species that live at these depths. The colossal squid and the giant squid are two of the most iconic examples. Their bodies stretch meters from tip to tip. Their eyes, adapted to the near-total darkness, are among the largest eyes known in the animal kingdom. Their tentacles reach outward into the dim water like long, searching limbs that sense movement far beyond their bodies. These animals are not fast in the way shallow water squid are. They don't dart or change direction suddenly. They move with controlled precision, each motion powered by muscles that conserve energy through the cold. Their size helps them endure the long intervals between meals, and their slow metabolism allows them to wait patiently for the right moment to strike. The deep sea is filled with similar patterns. Creatures we normally expect to be small become unexpectedly large in the abyss. Sea isopods, which look like oversized pill bugs, roam the seafloor with thick armoured plates and slow, deliberate movements. They can grow to the size of a house cat, far larger than their warm water relatives. The pressure doesn't crush them because their bodies are built with flexibility and toughness. Their large size isn't a luxury. It's a survival adaptation that helps them digest large meals slowly over extended periods without needing constant feeding. The same applies to giant amphipods. In shallow waters, these crustaceans are tiny, nearly invisible creatures that dart around with frantic energy. In the deep cold, they become much larger. Their bodies elongated and strong enough to withstand crushing pressure. They use their size to travel long distances across the seafloor in search of food. Their slow metabolism keeps them from burning their energy reserves too quickly. Every movement is calculated and every bit of food matters. Over years of steady living, their size becomes both a resource and a necessity. Even worms take on forms that challenge what we expect from animals with simple body plans. Deep-sea polychaete worms stretch several meters long, moving through the sediment with gentle, measured undulations. Their bodies can handle the extreme cold because their internal processes slow down so much that every cell functions at a careful pace. Their size helps them store energy and resist the cold, allowing them to live long lives in a place where rapid growth would be impossible. But gigantism in the deep sea isn't limited to familiar groups like crustaceans or mollusks. It appears in some of the simplest animals on Earth. Sea stars and sea urchins become enormous on the ocean floor. Some starfish develop thick arms that spread across large distances as they slowly crawl across the sediment. Their slow movement is not a sign of weakness. It's a sign of adaptation. They do not need to hurry. The deep rewards patience. Size gives them access to more food spread across wider areas and allows them to survive long periods between meals. Even jellyfish, creatures made primarily of water, grow to astonishing sizes in the deep. Some species have bells that stretch several meters across and tentacles that drift out into the water like impossible threads. Their slow pulsing movement matches the rhythm of the deep. They do not chase prey. They simply wait for something to come into contact with their tentacles, letting the environment deliver food in its own time. Their size is what gives them the reach to survive in such a sparse ecosystem. As we continue imagining this descent, it becomes clear that gigantism in the deep sea isn't a single adaptation, but a collection of interconnected advantages shaped by the environment. The cold slows digestion. The pressure supports and stabilizes large bodies. The energy scarcity encourages long-term storage. The oxygen, though less abundant in the deepest layers, is used efficiently because of slow metabolism. The animals here evolve toward forms that can endure isolation, starvation, and pressure. Over millions of years, the species that survive are the ones whose bodies match the demands of this place. Their size is not a luxury. It is the outcome of natural selection shaping life to fit a world defined by extremes. The abyss isn't just shaped by physical pressures, it's shaped by space itself. The deep ocean is vast, far more expansive than the surface waters most of us picture when we think about the sea. There is room here for creatures to spread out, grow wide, stretch long, and carve space for themselves in ways that shallow water animals cannot. In the shallows, territory is limited, resources are limited, temperature changes with the seasons. Predators move quickly. In the deep, everything is more predictable. The temperature remains consistently cold, the pressure constant, the environment stable. Unchanging conditions over millions of years create a world where slow and steady evolution works perfectly. Growth becomes gradual, generational, and uninterrupted. With stability comes longevity. Many deep-sea animals live far longer than their surface relatives. Some species of deep-water fish live for more than a century. Deep-sea corals, rooted calmly in the darkness, grow so slowly that some have been alive for thousands of years, and the longer an organism lives, the more time it has to grow. This steady build-up across decades causes the large sizes that seem out of place when compared to the rapid, short lives of many surface species. In the deep cold, size becomes the natural outcome of slow growth paired with long lifespan. The deep sea is also a place where predators rely on stealth rather than speed. This shift changes the entire dynamic of how size functions. In the surface world, being small and fast helps animals escape predators. In the deep, being small and fast is almost irrelevant. Visibility is limited. Movement is slow. Predators detect prey through vibrations or chemical trails rather than sight. Being large helps animals avoid becoming prey because it makes them harder to swallow, harder to overpower, and harder to break apart. Large bodies become a defense mechanism in their own right. A creature simply too big to bother attacking is more likely to survive. Another intriguing aspect of deep-sea gigantism comes from body composition. Many deep-water animals are built from tissues that handle pressure well. Some develop gelatinous bodies that compress easily under pressure, without sustaining damage. This jelly-like structure allows them to reach sizes that would be impossible for animals relying on rigid frames or stiff shells. Their shape shifts as pressure changes during vertical movements. Their mass supports a quiet lifestyle of drifting and slow pulsing motion. These gelatinous giants do not need speed. Their structure fits the deep perfectly. One example of this is the giant deep-sea jellyfish, known for its long, ribbon-like tentacles that extend outward in all directions. The animal floats through the darkness with a bell that expands and contracts slowly, using minimal energy to maintain its position. Its body is mostly water, but its scale gives it power by extending its feeding reach across a much larger area than a small jellyfish ever could. It survives by covering space, not by chasing prey. Another example comes from the deep-sea siphonophores. These organisms look like single creatures, but they are actually colonies of specialized individuals attached to one another. Some siphonophore species reach lengths that exceed those of whales. Their bodies stretch across the water like long, delicate cords. Each section plays a role. Some parts gather food, some handle movement, some handle reproduction. Their size is a direct result of a lifestyle built for drifting through a vast, stable environment where covering long distances helps them survive. The abyss encourages this kind of scale. It doesn't push life toward complexity for complexity's sake. It pushes life toward forms that make sense under extreme conditions. Slow metabolism, steady pressure, cold temperatures, and scarce food create a set of rules that reward large forms with slow, deliberate lives. If we consider the way the deep affects oxygen, the pattern becomes even clearer. While the cold surface layers of the ocean contain a great deal of oxygen, the deepest regions can be less oxygen-rich. At first, that might seem like a disadvantage for gigantism, but slow metabolism compensates for it. Large animals in the deep don't move fast enough to burn through oxygen quickly. Their cells use oxygen at a measured pace. Their bodies evolve structures that maximize oxygen absorption. Even when oxygen is scarce, these creatures survive because they manage it efficiently. The deep doesn't eliminate oxygen. It simply requires animals to become better at using small amounts over long periods. When scientists first discovered deep-sea gigantism, it sparked fascination and confusion. Why would such a difficult place produce animals of such extraordinary size? Over time, the answer became clearer. It wasn't one factor, but a combination of many. Cold temperatures slowed all biological processes. Pressure favoured sturdy structures. Food scarcity encouraged long-term storage. Stability allowed slow growth to accumulate. Predation favoured bodies too large to attack. Oxygen levels supported slow but steady life. When all these factors combine, the result is an ecosystem where large bodies thrive naturally. As we bring all these threads together, gigantism in the abyss becomes not a mystery, but an expected outcome of the environment's characteristics. The deep shapes life patiently. It doesn't rush anything. It encourages creatures to grow across decades rather than months. Their shadows appear enormous, not because nature became extravagant here, but because the environment chooses creatures that can thrive under pressure, cold, darkness, and scarcity. And as we continue following this story, the next steps lead naturally into how evolution uses these conditions to shape entire lineages over time, gradually reinforcing the traits that allow cold water creatures to become the immense forms drifting in these shadow depths. When we look at the enormous animals that live in the coldest parts of the ocean, it's easy to focus on their size as if it's a single trait that suddenly appeared. But evolution doesn't work like that. It doesn't hand out giant bodies all at once. It builds them slowly, generation after generation, using whatever the environment rewards. The blueprint for these large bodies didn't form overnight. It formed through countless small changes shaped by cold, pressure, stability, and the slow rhythms of life in these regions. When the conditions stay the same for long enough, evolution begins to carve a path that leads species toward forms that look almost impossible when compared to their warm water relatives. To understand how this blueprint forms, imagine a species living in a cold environment. The temperature is low year-round, the seasons are predictable, food arrives in pulses, oxygen is abundant, life moves slowly. In this setting, individuals with slightly larger bodies often survive longer. They can store more energy to survive the lean months. They can conserve heat more efficiently. Their slower metabolism consumes less energy. Their movements fit the thick water that surrounds them. They simply last longer in conditions that demand endurance instead of speed. These advantages don't appear all at once. They start with tiny differences. One slightly larger egg, one individual with a slightly slower metabolism, one creature with just a little more muscle or a slightly thicker body. In warm waters, that extra mass might be a disadvantage because it demands more energy. In cold waters, it becomes an advantage. When those individuals survive longer, they produce more offspring. Their traits spread through the population. Over generations, the average size increases. Evolution isn't forcing size onto them. The environment is gently nudging them toward bodies that fit the conditions better. This is how many cold water species began their journey toward gigantism. It wasn't because they needed to be large to dominate the ecosystem. It was because large bodies helped them survive the cold, store energy, and move through dense water more efficiently. Evolution simply responded to those benefits, reinforcing them where they appeared. Over long periods, these small changes accumulate. A species that was once modest in size gradually shifts toward larger, sturdier forms. The blueprint becomes clearer. If the environment remains unchanged for thousands or millions of years, as it often does in deep and polar regions, evolution has time to write this growth into the very structure of the species. It becomes a defining trait rather than a temporary adaptation. This is how many of the giant invertebrates in cold waters came to be. Their ancestors were small creatures living in environments where being tiny helped them dart away from predators or slip through narrow crevices in reefs. But when some of those lineages moved into colder, deeper regions, the rules changed. Speed mattered less. Hiding places were scarce. Predators were patient rather than fast. The old advantages of small size lost their value. The environment rewarded mass, endurance, and energy storage. Gradually the blueprint shifted. The genes that allowed for slightly larger frames spread. Over many generations, those frames expanded even further. For crustaceans, this evolutionary shift is especially clear. Crabs, amphipods, and isopods that migrate into cold waters consistently grow larger than their tropical relatives. Their exoskeletons become thicker, their limbs extend, their bodies expand to store more nutrients and withstand greater pressure. The cold not only supports these changes, it encourages them. Over evolutionary time, the species that embrace these traits become the giants of their environments. A similar pattern appears in mollusks. Squid, for example, evolved to be agile hunters in shallow waters, with quick movements and rapid metabolism. But in the deep cold, speed becomes less important. The colossal squid and giant squid represent lineages that took advantage of the cold stability and its oxygen-rich layers to develop slow, deliberate bodies. Their enormous size is a product of deep evolutionary pathways that rewarded individuals capable of endurance, the ability to drift silently for long periods, to store energy, and to survive the long, dark intervals between meals shaped their form far more than the need for speed ever did. Even creatures with very simple structures follow the same pattern. Sponges, for instance, don't have complex nervous systems or muscles, yet some species grow to impressive sizes in polar regions. Their growth pattern is slow but steady, and the cold waters help preserve their bodies for centuries. Evolution didn't need to rewrite their structure. It simply allowed them to grow larger over time because the environment supported longevity. These giant sponges are living examples of how evolution can produce enormous forms from simple beginnings when conditions remain stable, long enough for traits to accumulate. One of the most striking examples of evolution's blueprint in cold waters comes from the world of echinoderms, sea stars, sea urchins, and sea cucumbers. These animals often show extreme size variation depending on their habitat. In the tropics, many of them remain small and highly active. In the polar seas and deep cold, they grow steadily larger, thicker, and heavier. Their bodies reflect millions of years of environmental pressures that favoured endurance over agility. Their large sizes are not anomalies, but carefully shaped outcomes of living in a place that rewards slowness, steadiness, and mass. While the cold drives many of these changes, we also need to consider the role of evolutionary time. Cold environments tend to change slowly. They don't experience the same rapid fluctuations that warm regions do. Temperature remains stable, nutrient cycles repeat annually, pressure stays constant. This stability allows evolution to follow long, uninterrupted paths. Species living in fast-changing environments often evolve quickly, but in unpredictable directions. Species in stable environments evolve slowly but with clear, consistent patterns. In the cold deep, this slow evolution leads steadily toward gigantism. Over millions of years, this process creates a kind of evolutionary stacking effect. Each small advantage builds onto the previous one. Slightly larger individuals survive longer. Their offspring inherit genes that predispose them to slightly larger bodies. Those offspring grow a bit bigger. Over countless generations, this stacking results in bodies that look almost surreal in size. The blueprint wasn't designed all at once. It was assembled in layers, each one shaped by the pressures of the cold environment. But evolution doesn't only change body size, it also changes body structure. As creatures grow larger, their anatomy must adapt to support the increased mass. Muscles need to change. Circulatory systems need to become more efficient. Respiratory structures need to expand. Even the skeleton or exoskeleton must reinforce itself in new ways. In warm waters, many of these structural changes would be too expensive metabolically. The energy demands would outweigh the benefits. But in cold waters, slow metabolism spreads the cost over long periods. Structural changes that would be impossible elsewhere become feasible here. This is why many cold water giants have sturdy, thick bodies. Their evolution had the freedom to add muscle mass, reinforce joints, and expand internal organs. Their slow lifestyles allowed these changes to accumulate gradually without overwhelming their energy budgets. Over time, these adaptations became standard within their populations. The cold also shapes how species respond to predation. In rapidly changing ecosystems, Predators often evolve speed or agility to catch prey. Prey evolve similar traits to escape. This arms race favours smaller bodies adapted for quick movement. In cold waters, the arms race looks entirely different. Visibility is limited, and speed is less useful. Predators rely on ambush tactics or long periods of stalking. Prey rely on endurance, thick bodies, and the ability to survive for long stretches without food. Evolution responds by nudging species toward forms that support these strategies. Size becomes part of the survival toolkit rather than a burden. Another important evolutionary factor is how the cold affects reproductive strategies. Species in warm waters often produce many offspring because survival rates are unpredictable. In colder regions, survival depends more on endurance than speed, and species often produce fewer but larger offspring. These offspring have a higher chance of survival because they begin life with more mass and more stored energy. Over time, producing larger offspring perpetuates the cycle of increasing size in the population. The blueprint of gigantism becomes embedded not just in adult forms, but in developmental patterns from the earlier stages of life. Even migration patterns feed into this evolutionary framework. Many large animals, such as whales, rely on cold water feeding grounds to accumulate energy. Their evolutionary ancestors didn't start enormous. They expanded over generations as the cold supported their feeding habits and allowed steady growth. The blue whale's immense size isn't just a marvel. It's the product of millions of years of evolutionary refinement shaped by cold, nutrient-rich waters. Without those conditions, the largest animal on Earth could never have existed. Understanding evolution's role in cold water gigantism also reveals how fragile this blueprint can be. It took millions of years of stable environments to create these giants. The cold oceans provided predictable conditions that allowed slow, steady growth to succeed generation after generation. When creatures rely on long lifespans, slow metabolism, and gradual energy accumulation, rapid environmental changes pose serious risks. Evolution can guide species toward larger forms, but it can't adapt them instantly to new threats. This makes cold water giants especially vulnerable to disruptions in temperature, food supply, or oxygen levels. Despite this vulnerability, the evolutionary journey of these species demonstrates how powerful the combination of cold and time can be. It shows how life adapts when environmental pressures remain steady for long periods. The blueprint carved by evolution is not a rigid design. It's a flexible guide that shifts to match the conditions in which species find themselves. In cold waters, that guide consistently points toward large bodies capable of surviving slow, quiet lives. As we continue exploring the lives of these cold water giants, the next step leads us into the concept of time itself as it relates to the cold. How slow internal rhythms, extended lifespans, and the steady passing of years shape the creatures drifting through these icy worlds. When we follow the giants of the cold into the deeper patterns that shape their lives, one theme keeps appearing no matter which creature we look at. Time moves differently for them. Not literally, of course. The seconds pass the same, but the way those seconds feel inside their bodies is slower, quieter, and stretched across spans that would be unimaginable for most animals. In cold waters, time isn't something to outrun. It isn't something slipping away. It's something that unfolds gently, extended by every factor in the environment: the temperature, the pressure, the oxygen, the scarcity of food, and the slow metabolism that ties everything together. These giants don't just live in the cold. They live in a version of time shaped by it. When we picture time as most animals experience it, we tend to imagine urgency. A small fish in warm, shallow water must constantly stay alert. Predators move quickly. Prey escapes in sharp bursts. Food appears and disappears within moments. Even the water temperature changes from day to night. Life moves rapidly, and every creature must match that tempo. Their bodies are tuned to fast metabolism, quick decisions and short lifespans. Everything pushes them to hurry. Cold water giants live in an entirely different rhythm. Down in the icy depths, or even in the colder surface layers of polar seas, nothing changes quickly. The temperature stays steady all year. The currents move slowly. Food arrives in long cycles. Predators linger rather than sprint. Prey holds still rather than scatter, and the giants drifting through these regions respond with bodies that match that steadiness. Their internal clocks slow to a pace that would seem almost still to creatures living in warmer seas. The first sign of this slower time is lifespan. Many cold water giants live far longer than their warm water relatives. A small fish in tropical waters might live only a few years. A similar species in cold waters can live for decades. Some deep-sea fish have lifespans exceeding a century. Deep-sea corals grow for thousands of years. The Greenland shark, with its calm, unhurried movements and near-freezing body temperature, can live for multiple centuries. Its life stretches across eras, often outlasting entire human civilizations. Its size is not a rush toward greatness. It's the result of time unfolding at a pace that allows small increments of growth to build and build without disruption. This extended timescale shapes every part of these animals' lives. Growth becomes something that happens quietly and steadily. Instead of growing rapidly and stopping early, many cold water giants grow continuously. The amount they grow each year might be tiny, barely noticeable, but because they live so long, these tiny increments accumulate into the massive forms we see. Their bodies become large not because evolution pushed them to expand quickly, but because the environment gave them the luxury of time to expand slowly. If we follow this theme further, the slow pace becomes visible in their daily lives as well. A giant isopod on the deep-sea floor might spend long periods sitting still. It doesn't burn energy by wandering constantly. It moves only when something nudges it, or when the scent of potential food reaches its senses. A giant amphipod doesn't dash from one place to another. It inches forward through the sediment, saving energy, taking its time. A colossal squid doesn't chase its prey in bursts of speed. It waits patiently in the dim cold, letting the water bring opportunities to it. These creatures aren't lazy. Their bodies simply aren't designed for speed because speed wastes the precious energy their slow metabolism saves so carefully. There's also the way they handle reproduction. In warm waters, many species reproduce rapidly because lifespan is short and unpredictability is high. In cold waters, reproduction follows a calmer, slower pattern. Some species reproduce only once every year or even once every few years. Others produce fewer offspring, but each one is larger and given more resources to survive. Cold water giants don't rush to reproduce. They wait for the right conditions, often tied to nutrient cycles, seasonal light changes, or food availability. That patience is built into their biology, guided by internal cycles that turn slowly. Time moves through their daily actions as well. Digestion, for example, is a process we rarely think about as having a pace, but in the cold, it slows dramatically. A deep-sea giant isopod can gorge itself when food appears, a rare opportunity in the abyss, and then spend months digesting that meal. It doesn't need to feed again during that time. Its body processes the nutrients so slowly that a single meal can sustain it far longer than a warm water species could ever tolerate. Digestion itself becomes a long conversation between the animal and the environment, each bite stretched across time. Even the process of healing follows this slow pace. In warm waters, wounds must heal quickly or risk infection or predation. In cold waters, the slower metabolism means tissues rebuild gradually. Injuries take longer to repair, but the creatures here rarely face constant attack or competition that would demand quick recovery. The environment allows them to heal in the same steady rhythm they live by. These long, slow patterns shape how cold water giants experience the world around them. They don't react instantly to changes. They adjust gently to currents, to shifts in food availability, to new pressures in their habitat. Their bodies and behaviours aren't designed for rapid responses. They're designed for endurance, for survival drawn out across time, for longevity that supports their slow way of life. One of the clearest examples of this long relationship with time is the Greenland shark. Moving at a pace so slow it seems barely alive, its body temperature always close to freezing, it drifts through the cold North Atlantic with a calmness that feels almost unnatural. It grows incredibly slowly, just a few millimeters each year, but it never stops growing. Its metabolism is among the slowest known for a large animal, and because it grows so slowly, it lives an extraordinarily long life. Some individuals may be nearly 400 years old. Their perspective on the ocean, if such a thing could exist, would be shaped by centuries of movement through cold waters, unchanged by the rapid pace that countless other species experience. Another example is found in the huge Antarctic sponges. These animals grow so slowly that they seem frozen in time, but over centuries their bodies expand to enormous sizes. Their slow metabolic processes, steady internal rhythms, and the cold water's preservation all contribute to lifespans far beyond what we normally associate with animals that lack complex organs. Their size is a direct reflection of time accumulated rather than rapid growth. Even the colossal squid, one of the more formidable giants of the deep, reveals the same reliance on slow time. Its growth is measured in small yearly increments. Its life revolves around waiting rather than chasing, drifting rather than darting. Its enormous body forms over many years of calm existence. The cold doesn't demand speed, it demands patience, and the squid exemplifies that perfectly. One detail that ties many of these giants together is how stable their environment remains over long stretches of time. Warm waters change quickly, temperature shifts can happen daily, storms stir the surface, seasons bring dramatic changes. In cold, deep waters, conditions are almost constant. Temperature doesn't fluctuate much, pressure is steady. The absence of light removes day-night cycles. Food cycles are slow but predictable. This stability gives creatures the security to invest in long-term strategies. They don't need to live fast because their world rarely forces them to. The environment sets a slow tempo, and evolution tunes their bodies to match it. Because of that, cold water giants often become creatures defined by their patience. They are built for lives that unfold across vast timescales. Their stories aren't measured in days or months, but in decades and centuries. Their size is a physical record of time accumulated. Each millimetre of growth reflects a year or more of life lived quietly in the cold. When we imagine these creatures moving through their frozen wilderness, a different sense of time emerges. We picture them drifting, resting, crawling, pulsing, or gliding without any urgency. Their movements blend into the environment, matching the slow rise and fall of currents. They look almost like memories drifting through the water rather than living animals, because their pace is so different from what most of the world recognizes as life. But this slow pace is not a weakness. It's their greatest strength. It allows them to survive conditions that fast-moving species never could. It lets them endure long periods without food, recover from injuries slowly but effectively, and persist through environmental changes that occur over centuries. Time becomes their ally instead of their enemy. Even their sensory systems reflect this slow relationship with time. Many deep-sea giants don't rely on rapid visual signals. In the darkness, vision becomes less useful. They sense pressure changes, chemical cues or vibrations, signals that arrive slowly through dense water. Their reactions match the pace of the information they receive. They process their surroundings in a way that resembles listening rather than watching. The cold slows even the flow of information through their bodies, giving them a calm, grounded perspective on their world. When we observe this slow timescale in action, it becomes easier to understand why cold water giants are so vulnerable to sudden environmental change. Their entire existence relies on stability. Sudden warming or rapid shifts in oxygen levels disrupt the slow rhythms they depend on. But understanding that vulnerability also underscores how perfectly adapted they are to the world they inhabit. Their lives are shaped by a kind of patience that most species would find impossible. As we keep moving forward in this story, the next step connects the slow internal rhythms of these giants with the wider ecological relationships that shape their interactions. Their size, their slow metabolism, and their extended lifespans influence not only their individual survival, but also their roles as predators, scavengers, and competitors in the frozen wilderness. When we think about predators and prey, most of us picture quick movements, sudden attacks, bursts of speed, and frantic escapes. That kind of dynamic is familiar in warmer waters, where metabolism runs fast, bodies stay small, and life depends on reacting within fractions of a second. But in the cold regions of the ocean, the relationship between predators and prey takes on a different tone. There is an arms race here, but it's not loud, it's not frantic. It's a slow and steady contest shaped by the pace of the environment, by the thickness of the water, by the scarcity of food, and by the long lifespans of the creatures that drift through it. The cold doesn't eliminate competition. It simply stretches it across time until the interactions become quieter, heavier, and more deliberate. In warm waters, the arms race often revolves around speed. A predator evolves faster muscles. A prey species evolves quicker reflexes. Predators refine their agility. Prey sharpen their evasive maneuvers. The environment rewards immediacy. A fraction of a second can determine who lives and who dies. In cold waters, that quickness loses its value. Cold slows muscle contraction. It slows nerve signals. It slows chemical reactions. It slows metabolism. It doesn't matter whether a creature wants to move fast or slow. The environment decides for them. Everything here operates at a reduced pace. Because of that, the arms race takes a different shape. Predators don't try to outpace their prey. Prey don't try to outrun predators. Instead, both sides rely on endurance, patience, size, and strategy. The cold encourages larger bodies, which changes every aspect of predation. A large predator doesn't need to chase quickly. It needs to wait. A large prey animal doesn't need to dart away. It needs to be difficult to overpower or swallow. Survival here is built around the idea that the creature with the more efficient long-term strategy wins, not the one with the faster movement. One of the most striking examples of this quiet arms race appears in the relationship between large deep-sea predators and the creatures they hunt. A colossal squid drifting through the cold depths does not rush at its prey. It uses its large eyes to detect faint glimmers of movement far away. It hovers calmly, conserving its energy, watching for the right moment. Its limbs are powerful, but they aren't built for rapid chases. They're built for gripping and holding prey once it gets close enough. The squid's prey, often large deep-sea fish or other sizable creatures, don't rely on speed to escape. Instead, they rely on thick bodies, strong muscles, and the ability to resist an attack long enough to slip away in the darkness. When these animals meet in the cold, the interaction isn't a blur. It's a slow, heavy struggle between two large creatures shaped by an environment that discourages haste. The same dynamic appears among crustaceans. In warmer waters, many crustaceans survive by darting rapidly across the seafloor, hiding in crevices and sprinting away from danger. In the cold seas, giant isopods and amphipods don't rely on quickness. Their bodies are too large for that. They depend on armoured shells that can withstand attacks, and on the ability to remain motionless when necessary. Their predators, often large fish or bigger crustaceans, don't sprint after them. They wait for an opportunity to strike when the prey isn't expecting it. The cold limits the possibility of sudden motion. Both predators and prey adjust by developing bodies and behaviours that emphasise defence and endurance rather than reaction speed. This slow-paced arms race also shows up in how animals hunt. In warm waters, many predators employ active hunting strategies. chasing schools of fish, ambushing quickly, or cornering prey with bursts of speed. In cold waters, predators rely on stillness. They creep closer using tiny, almost imperceptible movements. They use the darkness and the thickness of the water to their advantage. A large predator might drift silently for hours before making a move. Their prey in turn develop senses attuned to subtle shifts in the water rather than visual cues. They learn to detect the faint pressure changes created by a predator's slow movements. The result is a kind of sensory competition where each side tries to stay just a little ahead of the other, not through speed but through sensitivity. In the deep sea, where light doesn't penetrate at all, the arms race becomes even more focused on endurance. Many predators here don't need to hunt frequently. They eat rarely but in large amounts when they do. Their prey adopt similar strategies, growing large enough to store energy, staying still to avoid detection, and relying on long-term survival rather than short-term decisions. In this environment, a predator that can survive for months between meals has an advantage over one dependent on frequent feeding. A prey animal that can endure long periods without food will outlast competitors that require constant nourishment. The cold pushes both sides toward bodies that handle scarcity better, and larger bodies accomplish that more effectively. Another important part of this quiet arms race involves how both predators and prey manage their energy. In warm waters, animals burn energy at a rapid rate. Predators must catch multiple meals each day to survive. Prey must evade predators often enough to stay alive. In the cold, energy moves through the ecosystem differently. Everything slows. A predator may go long stretches without finding food, so it must conserve energy to survive. Prey must do the same. The cold waters reward strategies that minimize energy use. Large bodies help because they can store more energy and lose less heat relative to their volume. Over time, evolution shapes both sides into creatures that survive by enduring rather than by competing in bursts of activity. The giant sea spider is a good example of this. It moves slowly across the seafloor, feeding on small invertebrates or detritus. It doesn't need to escape predators by sprinting. Instead, its large body and long legs offer reach and stability. Predators that encounter it don't bother to chase it down because there's nothing to chase. Everything here moves at the same slow pace. So the arms race isn't about who can accelerate faster, but about who can last longer. In environments closer to the surface but still influenced by cold temperatures, the arms race becomes more about timing. Many cold water fish rely on seasonal cycles to feed. During periods when plankton thrives, or when prey species gather in shoals, predators take advantage of the influx of food. Prey evolve to synchronize their reproductive or feeding behaviors with these cycles, increasing their survival probability. Predators evolve to anticipate those cycles. The cold ensures these cycles remain predictable, and evolution uses that predictability to fine-tune behaviors on both sides. At the same time, the scarcity of food in many cold regions creates a competitive environment where stealing becomes as important as hunting. Scavengers grow large because being the first to reach a food source isn't as important as being able to dominate it once they arrive. In the deep, when the carcass of a dead whale reaches the seafloor, it becomes the center of a slow but intense competition. Giant isopods, large amphipods, massive worms, and sometimes even sharks gather to feed. There is no rush. The food will last a long time in the cold, but larger animals gain an advantage simply because their bodies allow them to consume more and protect their feeding spot more effectively. Prey and predators become interchangeable in this setting. Many creatures here play both roles at different times. In cold surface waters, such as the polar oceans, seals and whales participate in a slow arms race with their prey as well. Seals develop streamlined bodies and thick insulation that allow them to remain submerged in icy water for extended periods. Their prey, often fish or squid, evolve patterns of movement and body shapes that help them evade capture, not through speed, but by blending into the dim environment or by forming dense schools that confuse predators. Whales, in turn, use cooperative feeding techniques, slow, coordinated behaviours that take advantage of prey clustering. These behaviours evolve over long periods in environments where rapid change rarely occurs. Another fascinating example comes from the interactions between large predators and smaller prey in the deep waters of the Southern Ocean. The cold here encourages large bodies in both predators and prey. Some species of Antarctic fish develop antifreeze proteins that allow them to survive in temperatures that would kill most fish. Their predators, such as seals or larger fish, evolve jaw structures and feeding behaviours that enable them to hunt prey that moves slowly through the cold but is often well camouflaged or heavily armoured. The arms race becomes a slow, steady exchange of adaptations: thicker skin, stronger jaws, improved camouflage, better energy storage, and more efficient movement in dense water. Even microorganisms participate in this quiet arms race. In cold waters, bacteria and small organisms grow slowly. Their predators, tiny filter feeders or small invertebrates, adjust their feeding strategies accordingly. Instead of sweeping rapidly through the water for quick meals, they filter continuously but slowly, relying on the steady flow of cold, oxygen-rich water to bring nutrients to them. Over time, their structures evolve to maximize this slow, steady feeding rather than fast bursts of consumption. The arms race becomes a negotiation between efficiency and endurance. One of the most important aspects of this slow arms race is how it reduces the emphasis on agility. Warm water ecosystems reward small bodies with fast movements because those bodies heat up, cool down, and react quickly. In cold waters, agility offers limited advantages. Even if a creature could move fast, the thick near-freezing water would sap that speed quickly, and the energy cost of rapid movement would be too high. As a result, evolution doesn't reward speed. It rewards strategies that involve conserving energy, growing larger, enduring long periods of scarcity, and withstanding the pressure and cold. Predators learn to ambush or scavenge. Prey learn to become harder to kill, harder to swallow, or harder to find in the dimness. Size itself becomes a central part of the arms race. In warm waters, being small helps animals hide and move easily. In the cold, being small often becomes a liability. Small bodies lose heat quickly. They can't store much energy. They struggle to survive long gaps between meals. Larger bodies do better simply because they handle the cold and scarcity more effectively. Predators and prey both adapt in this direction. Over generations, the cold shapes entire lineages into larger forms, not because being large is inherently better, but because it fits the slow, deliberate strategies that life in the cold demands. This slow arms race has one more important feature. Cooperation emerges as often as competition. In some cold water environments, resources are so limited that species evolve behaviours that help them survive together. Whales feed cooperatively. Penguins huddle for warmth. Fish school to create confusing patterns that reduce predation. Even some invertebrates cluster together around food sources in a way that allows multiple species to survive in proximity. The cold doesn't eliminate conflict, but it does encourage strategies that share the burden of survival, rather than relying on constant aggression. Seeing all of these patterns together, the quiet arms race of the cold becomes clear. Predators and prey don't compete through rapid escalation. They evolve slowly, shaping their bodies and behaviours over thousands or millions of years to match an environment where time stretches out, food is scarce, and energy must be guarded carefully. Their adaptations flow into one another. The predator grows larger because the prey grows larger. The prey becomes sturdier because the predator becomes more powerful. The predator waits longer because the prey moves slowly. The prey relies on blending into the environment because the predator relies on detecting faint cues. This slow negotiation between survival strategies forms the backbone of life in cold waters, and as all of these interactions unfold in the frozen wilderness, They influence not just individual species but entire ecosystems. Every shift in size, metabolism, or behaviour affects the creatures around it. The quiet arms race ripples outward until it shapes the giants, the scavengers, the filter feeders, and even the smallest inhabitants of the cold. As we move onward, these ecological interactions naturally lead into another part of the story. How humans, when they venture into these frozen realms, encounter creatures whose size, slowness, and endurance reflect a world built on entirely different rules. When humans first began pushing toward the coldest reaches of the planet, they didn't come expecting to find giants. They came chasing fish, chasing fur, chasing trade routes, chasing knowledge. They came in wooden ships, then steel ships, then icebreakers, and eventually submarines and research stations. But almost from the moment humans reached the high latitudes, they encountered animal lives that defied their expectations. The further they pushed toward the edge of the world, the more they realized how different life in the cold truly was. These were not miniature, fragile versions of familiar creatures. These were colossal beings shaped by the extremes, existing on scales that made early explorers wonder how such animals could grow so large in such unforgiving places. The first encounters with these giants were often accidental. Sailors would report strange shapes rising from the darkness beneath their ships, a massive shadow drifting under the hull, a long tentacle brushing the surface, a sudden movement in the dim, icy water just at the edge of vision. In an era when humans knew almost nothing about what lived beneath the polar ice, every sighting carried a sense of mystery. Some early accounts describe whales so large that they seemed like moving islands. Others describe squid arms long enough to wrap around small boats. Even if these descriptions were exaggerated, the animals that inspired them were real, and they were truly enormous. Whalers in the North Atlantic were among the first to see these giants up close. Their work brought them face to face with bowhead whales, immense mammals with thick layers of blubber, long lifespans, and bodies built to endure ice-choked waters. The size of these whales astonished the men who hunted them. Bowheads could reach lengths longer than 2 houses placed end to end. Their skulls were powerful enough to break ice more than 1/2 meter thick. Their bodies carried energy reserves that allowed them to survive seasons of darkness. These encounters forced humans to recognize that the cold didn't shrink life. It expanded it in ways that defied assumptions. But whales were only the beginning. As human exploration moved southward into the Antarctic, the pattern repeated. Early expeditions encountered animals that seemed oversized, out of proportion, as if they had stepped into a different evolutionary world. Penguins that stood as tall as a child, seals with bodies that weighed more than a small car, squid with long, sinewy limbs and eyes larger than grapefruits. The explorers wrote about these animals in their journals, trying to understand how creatures living in such extreme cold could grow so immense. For many of the people who travelled to these remote places, meeting these animals wasn't just a surprise. It was a moment that shifted their understanding of life on Earth. They began to see that the cold didn't quiet life. It concentrated it. It slowed it. It shaped it into forms that didn't exist elsewhere, and humans became witnesses to this process. Scientific expeditions brought even more surprises. When researchers began sending trawls deep into the waters around Antarctica, they brought up invertebrates of staggering size, giant sea spiders with legs that stretched wider than a dinner plate, amphipods as large as a human hand, isopods as big as small animals. These weren't mythical monsters. They were ordinary animals pushed to extraordinary sizes by the conditions of the cold. Suddenly, the idea of gigantism in cold waters wasn't speculation. It was documented reality. At the same time, deep-sea exploration introduced humans to giants from the abyss. Submersibles captured the first images of the colossal squid. Not a fast-moving creature, not a dramatic hunter, but a slow, heavy, immense animal whose existence had been hinted at only through fragments found in the stomachs of whales. Seeing these creatures alive in the cold darkness revealed how little humans knew about the frozen wilderness beneath the waves. The deep didn't just hold secrets, it held entire ecosystems built around a scale humans weren't accustomed to seeing. As humans spent more time in these remote regions, they began to understand how the giants fit into the broader ecosystem. They observed how whales returned each year to feed on krill swarms that stretched across the ocean like drifting continents of life. They watched seals dive into icy waters with bodies insulated by thick layers of fat, disappearing for long periods before resurfacing with prey. They saw giant seabirds circle above the waves, travelling thousands of kilometres across the Southern Ocean. Each of these interactions painted a picture of an environment where size wasn't an anomaly. It was a requirement. Many scientists who study polar or deep-sea ecosystems talk about how strange it feels when they first meet these animals. Not because the creatures are monstrous or intimidating, but because they move with a calmness that makes them seem older, slower, and more deliberate than animals elsewhere. A massive seal will often watch a researcher with quiet curiosity. A large fish might drift near a submersible, observing it for minutes without reacting quickly. Even the enormous invertebrates move at a pace that feels measured. These encounters remind scientists that the cold changes not just the body, but the behaviour and the entire rhythm of life. This rhythm becomes even clearer when humans observe the life cycles of the giants. Researchers tracking the movements of bowhead whales discovered individuals that had survived for more than a century. Some may have lived well over 150 years. Their immense bodies are a kind of living archive of the Arctic environment, shaped by cycles of ice and migration that stretch across generations. When humans meet such a creature, there's a realization that they're encountering not just an animal, but a life whose timeline extends far beyond any human experience. The same is true for the giant Antarctic sponges, some of which began growing before many modern nations existed. Their size tells a story of slow accumulation, of growth measured in centimetres across centuries. When researchers dive near these sponges, they often describe a sense of stepping into a place where time has almost stopped. The animals do not rush. They do not compete aggressively. They simply persist, growing year after year in the cold stability of their environment. At the same time, scientists studying deep-sea sharks, such as the Greenland shark, realize they are meeting animals whose lifespan dwarfs human history. Some of these sharks may have been born during the era of Shakespeare. Meeting a creature that has lived through so much time creates a sense of humility. It forces humans to acknowledge how different life in the cold can be. While human lives are short and fast, the lives of these giants are long and unhurried. Yet despite their size and longevity, many of these animals are vulnerable. Humans discovered them only recently in the grand scope of time, but their existence hangs in a delicate balance. Because they grow slowly, reproduce slowly, and depend on stable conditions, disruptions to their environment can affect them deeply. Warming waters can shrink habitats that took millions of years to shape. Reduced ice cover affects the food webs that sustain whales and seals. Overfishing threatens the balance that supports giant invertebrates in cold regions. Pollution drifts into deep waters and settles on the seafloor, affecting animals that have no defense against it. When humans encounter these giants up close, whether through research, conservation work, or exploration, there's often a sense of responsibility that follows. The more people learn about the lives of cold water giants, the clearer it becomes that understanding them is only the beginning. Protecting them requires recognizing how fragile their world really is. Many scientists describe a moment when they first realize this fragility. It might come while watching a whale feed, thinking about how much energy it takes to grow such a massive body, or while examining a deep-sea specimen, realizing how slow its metabolism must be and how difficult it would be for the species to recover if its population declined. Or while watching an iceberg carve into the ocean, knowing that changes in temperature could disrupt the rhythms these giants depend on. Even beyond scientific circles, humans who encounter the cold giants, photographers, divers, sailors, explorers, often express a sense of awe, that stays with them long after they return home. Not awe in the sense of fear, but awe in the sense of respect. Seeing a creature that has evolved to survive the cold through slow growth, endurance and size reveals something profound about life on Earth. It pushes humans to think about time differently, to think about survival differently, and to think about how environments shape the creatures that live within them. These encounters leave humans with questions about their own place in the story of life. Why do some species grow quickly and die young while others grow slowly and live for centuries? How does cold sculpt bodies in ways that create such impressive forms? What does it mean for human understanding when the largest animals on Earth depend on some of the harshest environments? The cold giants don't offer answers directly. They don't communicate their histories or intentions. But by observing them, humans learn how powerful environmental forces can be. They learn that life thrives not only in warmth and abundance, but also in darkness, pressure, and scarcity. These giants become reminders that Earth is far more diverse than most people ever see. And as humans continue to explore the frozen edges of the world, they gradually piece together the story of how these colossal lives came to be. They discover how the cold amplifies bodies, slows time, stabilizes ecosystems, and creates relationships between predators and prey that unfold across decades rather than moments. Every expedition adds another detail, another layer to the understanding of how life functions in these icy realms. While humans study these giants, they also begin to see how their own activities intersect with the frozen wilderness. The world that supports these animals is changing, and understanding their lifestyles becomes more than just scientific curiosity. It becomes a guide for protecting ecosystems that hold some of the most unique life on the planet. As the story continues forward, all of these human encounters with cold-water giants point toward one final reflection: what it means to witness such enormous lives drifting beneath the ice, and how the cold shapes a world that feels both familiar and entirely alien at the same time. When we drift back into the quiet cold where these giants live, it becomes clear how different this world feels from everything familiar on land. The surface of the ocean might be restless, with winds shifting and waves rolling, but beneath that surface lies a steady, unhurried wilderness shaped by cold, darkness, and time. It is a place where heavy bodies move slowly, where sound travels softly, and where the creatures floating through the blue twilight carry the weight of millions of years of evolution in their shapes alone. Spending time imagining this environment makes it feel almost like entering another timeline, one with different rules, different rhythms, and different expectations of what a life can become. The giants drifting beneath the ice don't try to impress anyone. They don't perform for attention or display their size with confidence. To them, their immense bodies are practical. Their slow pace is ordinary. Their longevity is just part of the world they belong to. These animals aren't symbols. They're simply following the patterns of cold water, of low metabolism, of slow growth, of energy stored carefully across long seasons. Every movement they make, even the smallest one, reflects how closely their lives have been shaped by the environment around them. When people think about the extremes of Earth, they often picture volcanoes, deserts, or mountains. But the cold seas, especially the deep and polar ones, are extremes of a different kind. Instead of violence or intensity, their extremity lies in stillness, in silence, in patience. The animals here don't need to rush because nothing in their world demands it. The temperature never swings wildly, the seasons shift slowly. The food arrives on long schedules shaped by ice and sunlight. And all of these conditions allow life forms to evolve in ways that feel almost impossible when compared to warm, fast-moving ecosystems. Drifting alongside these giants in our imagination, it becomes easier to see how they fit into this frozen wilderness. A colossal squid resting in the dim blue doesn't look monstrous. It looks calm, its arms positioned with quiet control. A massive isopod crawling across the seafloor seems more like a careful traveller than a scavenger. A bowhead whale gliding beneath the ice doesn't feel imposing. It feels like part of the landscape, moving with the same steady rhythm as the drifting ice above it. Their movements repeat the pulse of the ocean, slow and steady, shaped by the cold that surrounds them. The more time we spend with these animals, even in thought, the more their size stops feeling surprising. When every part of the environment rewards endurance and mass, when survival depends on storing energy and conserving heat, when scarcity stretches across seasons, and when pressure and cold stabilize the ecosystem, large bodies become the natural answer. Gigantism stops feeling unusual. It feels inevitable. It's interesting to imagine what it might feel like for one of these giants to live through decades of cold. For a Greenland shark, which might swim slowly through the same waters century after century, the world must seem almost unchanging. The ice shifts overhead. The currents alter slightly over the years. The prey moves in cycles measured in seasons, but nothing happens quickly. Each moment of movement, each shift in temperature, each encounter with other creatures takes place in long intervals. The shark's body, built for slow metabolism and long lifespan, matches that pace naturally. Time doesn't rush forward for it. It stretches out, long and quiet. A similar thought applies to the enormous Antarctic sponges anchored to the seafloor. Their growth, so slow that years go by with barely any visible change, seems frozen. But when we imagine their lives spanning centuries, their impressive size becomes easier to understand. They grow because nothing interrupts them. The cold keeps everything steady. They persist because the environment doesn't challenge their existence with sudden changes. They simply continue, inch by inch, building their strange, massive structures over a timeline that dwarfs human lifespans. The giants of the cold aren't isolated individuals. They're part of a network of lives tied together by the slow movement of energy. Krill swarms feed whales. The fall of organic matter from surface waters feeds deep-sea invertebrates. Scavenging communities gather around carcasses that drift down from above. Predators move according to patterns set by prey that themselves follow cycles of light and temperature. Every creature relies on every other, and the cold keeps these relationships stable over long spans of time. Thinking about these interconnected lives, it becomes clear that the cold giants aren't just fascinating because of their size. They're fascinating because their existence reveals so much about how ecosystems work when time slows down. The stability of the cold makes everything more deliberate, more measured. Predators don't rely on rapid pursuit. Prey doesn't rely on sudden escape. Growth isn't rushed. Reproduction isn't frantic. The entire system leans toward a gentle balance, where endurance matters more than speed, and where patience becomes the defining trait of survival. If we imagine ourselves drifting with these giants, perhaps gliding through cold blue water in a quiet moment, we'd probably notice how quiet everything feels. Sound doesn't travel in sharp bursts. Movement doesn't happen in sudden waves. Even the flicker of small organisms drifting past doesn't break the stillness. The water absorbs noise. The cold slows reactions. The pressure keeps everything heavy and calm. Surrounded by this environment, the giants look like they belong to a world that moves at half speed compared to our own. Humans rarely think in slow time. Most of what we do relies on rapid decisions, quick changes, and short-term goals. But the cold oceans show us a different way of existing, a way where life expands steadily across decades, where energy flows carefully through long cycles, and where creatures grow massive not because they rush, but because they don't. Being close to these giants, even just in imagination, can shift how we think about life's possibilities. It also highlights how fragile these giants truly are. Their slow metabolism makes them resilient in the cold, but vulnerable to rapid change. Their long lifespans give them endurance, but make it harder for populations to recover quickly. Their stability depends on environmental conditions that remained relatively constant for millions of years, and sudden disturbances ripple through their world more intensely than through fast-moving ecosystems. When waters warm or nutrients shift or ice disappears, the slow pace that once protected them becomes a disadvantage. They can't adapt quickly. They can't change their strategies overnight. Their endurance becomes fragile under pressure. Thinking about this fragility doesn't diminish the awe they inspire. If anything, it deepens it. These animals survived ice ages, survived deep-sea pressures, survived food scarcity, survived conditions so cold and dark that most species would perish instantly. Their existence reveals a different kind of strength, one built on patience rather than power, one built on slow growth rather than speed, one built on quiet persistence rather than aggression. Drifting through the cold with them, even for a moment in thought, makes us reflect on how complex life can be, and how many ways evolution can solve the problem of survival. In the frozen wilderness, size becomes a kind of certainty. A giant body stores energy, conserves heat, withstands pressure, and carries the animal across years where changes happen slowly. This certainty supports every aspect of their lives. The cold amplifies their bodies not because it demands gigantism, but because it rewards the traits that eventually lead to it. If we imagine ourselves suspended in that cold water, watching a massive creature pass by in silence, it doesn't feel like an encounter with something monstrous. It feels like witnessing a piece of the environment itself. Its movements are as steady as the currents. Its pace matches the drift of sediment. Its presence fits into the landscape the way a mountain fits into its surroundings. Giant animals aren't out of place in the cold. They are the natural outcome of its rules. As we drift there in thought, surrounded by the vastness of the frozen sea, the idea that cold breeds giants stops being surprising. It becomes almost obvious. The cold shapes life slowly. It trims away the need for haste. It encourages bodies that endure. Over endless generations, those slow pressures accumulate until the creatures that survive carry the mark of that environment in their sheer scale. And if we continue drifting with them just a little longer, letting the calm of their world settle in, it becomes easier to understand why these giants matter. Not only for what they can teach us about biology, but for what they reveal about the many ways life can grow on this planet. Their existence reminds us that evolution doesn't follow one path. It adapts to whatever the environment gives it. In the cold, the environment gives it time, quiet, stability, and energy that moves slowly. And from those ingredients, it shapes some of the largest and most remarkable animals Earth has ever seen. Drifting beneath the ice, surrounded by the calm pulse of the cold world, these giants continue on their steady paths, carrying the story of their environment in every movement. Nothing rushes here. Nothing pushes forward more quickly than it needs to. The cold sets the pace, and life follows, stretching across years and centuries in ways that feel almost impossible from the surface. And as we let that image linger, the story continues on in the same gentle rhythm, moving forward with the quiet understanding that the cold seas still hold more secrets, more giants, and more slow-drifting lives waiting deeper in the blue.